Good afternoon, Professor.
Good afternoon. Thank you for saying so. Good afternoon. Good afternoon, indeed. Okay, here we go. Yes, good afternoon, Liani, and good afternoon. Good afternoon, Jitlali. Good afternoon, Antonia. Oh, it's like all good afternoons now. It's crazy.
Good afternoon, Professor.
Good afternoon, Juanita. Thank you. Good afternoon, Michelle. Good afternoon, David. Wow, okay. Oh, good afternoon. It's like all good afternoons. This is like a crazy new. Well, all right, everything is okay. Good afternoon, Vince. Did I say that? Okay. Hi, Tomika. Okay. Good afternoon, Shankia. Good afternoon, Shomari. Okay. Oh, more people. Sorry.
Morning, Professor.
Yeah.
Or evening, my bad.
Good morning, Caleb. Thank you. Good. All right, awesome. All right, I think we're all, we're going to start second. We're going to start second. Oh, good afternoon, Jacob. Thank you. That's awesome. Good afternoon. Why am I? Okay. Oh, more people. Hold on. Okay. Oh my God, what is that? Well, that's. Yeah. Oh, good. Oh, yes. Good afternoon, Jacob. I think I said that. Sorry. Yes. Good afternoon. Okay. We are okay. Super quick, and I'm going to be super quick. And again, from here on in, so it's great to see you all. I already miss you. Some of you already mentioned in a side chat or like a thing, like there are some of you I even have in mind. I might not ever spend it to you specifically, but I'm definitely delighted to write a recommendation. I mean, I'm delighted to write recommendations for people who need them. And I think a couple of people mentioned them. We never followed up. Like, just text me later privately and we'll work it out. I'd be delighted. Everything from here on in is please text to me and we'll work it out. I mean, you can email, but text will be faster. Oh, okay, more people coming in. Sorry. Good afternoon, Wayne. Good afternoon. Again, for the last time, just in case, I'm putting it in here. So from here on in, it's like text me for whatever. Oh God, I'm gonna forget. Hold on 1 second. Sorry, hold on. Okay. I will try to post the final as quickly as I can after class today. Technically, I still have till 7 p.m. tonight. Like I said, it would be up by 7. I'm going to try to do it much faster than that. I am going to try, but just bear with me. It'll look very much like what's in. Sorry, people still coming in. The final will look remarkably similar to what's in the Google Classroom right now. If you look, I've updated twice. What you should find when you look is version 3. I think it has 25 questions now. I think that's where it's going to stop. Wait, it's either 20 or 25. And I'll adjust the point values. It's meant to be 100 points. I think right now it's 125 points just because I didn't adjust. But and if I forget to adjust, don't overthink that. Like it's whatever. It's going to be remarkably similar to the version 3 that you see now. So if you want to have that next to you while you try to take notes or try to listen to me for the next 2 hours, that might be not a bad idea. Again, you're going to have till Saturday noon to do it. Again, it shouldn't hurt you really. It's meant to help you. I mean, like it's going to count and all of that, but it should. Good afternoon. Awesome. Blah, 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 blah. You, again, even though it's true, false and all that, and I don't want to see any work, you can talk to one another. That's not cheating. But then after you talk, but be careful. I mean, don't trust people just because they say something. Like the questions are hard. I think the material is hard. You can look things up on the web, but you got to really be careful when you translate those questions and look them up on the web. Like for real, they're not meant to be tricky. or they're not meant to be tricks, but they are tricky. So you can help each other and whatnot, but I will warn you what, and so it's due Saturday at noon. I probably won't answer questions about it from here and there, but I'll answer questions, whatever stuff you need, or grading things, whatever. What was I going to say? One thing to caution you though, again, I'll just want it by Saturday noon. You can submit it at any time and it should auto grade and it should return itself to you right away. So you should be able to have a sense of what your grade is right away. The grades are due from me to CUNY first by Monday or Sunday night. So I'm going to try to, that's why I'm doing this all quickly like this. One thing just to warn you, well, two things. One, if you try to do that, the final, once you get it, if you try to download it, try to enter it, and it says like you don't have permission or something, that shouldn't happen. But if that does happen, text me right away and let me know. That can happen with Google Forms. The other thing is, because it's a final exam, again, you can do as many drafts as you like. You can talk to other people and stuff, but once you hit submit, it's not going to let you edit it or do it again, because it is a Google Forms and it is technically a test and all that stuff. So I do want to warn you that once you hit it, and then it goes into me and it probably self-grades. So please be careful about that. Like, don't actually submit it until you're pretty sure you know what you're doing. And I will warn you, this is not meant to be blah, 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 but the questions will be scrambled. I mean, the order will be scrambled. So even if you work with someone else and try to work on it, don't be naive. I mean, don't just like copy their TF and put it into yours, because the order will be different. So you do want to think through the questions. Okay. Again, it's meant to help, not to hurt, but it is meant to force us all to learn some physics right at the end. Okay, chat. And I am, okay. Again, from here on in, any concerns about grading or anything like that, please text me. I don't really want to get into that in this last day. I do want to just teach physics. I'm gonna try to write down, I'm gonna try to use the notes as I usually do. In fact, to remind myself. But I have a lot to say. I think it's interesting. I don't think it's easy, but I'm not, I have a lot to say and I'm going to say it. I'm going to use my 2.5 hours to just like vomit on you. We said the course gets faster and faster as it goes. Today is the fastest day in a way. I'm not going to do a lot of calculations. Don't worry about that. Like, a lot of what I'm saying is super mathematical, but conceptually mathematical, if that makes sense. It's not going to be number crunching. It's going to be ideas. Just please do try to bear with me and follow. I'll try to write stuff down. But if I get really racing or absorbed, please, you take notes for your own sake, for the future, for the final, whatever. Like, and then you can play the tape again, of course. We are recording, right. Okay, yeah. So that's, I mean, I'm protecting myself because I know once I get lost in this physics, it's just going to be physics for 2.5 hours. Again, you can come and go if you need your brain to take a break, but I don't want to take a break. I'll also say something that I have really enjoyed this class. I think you guys have been great. I think you've done a great job under really hard circumstances. I mean, COVID, 5 weeks, physics, all that. Some of you are from John Jay, some of you are not. I think you've been terrific. I will miss you. Those of you who go to John Jay, I'll also tell you, here's what's weird. One of the reasons I'm also being frantic, like, my people at John Jay don't even know what I'm about to say, but actually my family and I are leaving Brooklyn like tomorrow for at least a year, if not the rest of our lives. I'm going to continue working at John Jay as best as I can and remote and all that, but we're actually like moving like hundreds and hundreds of miles away tomorrow. So I'm still going to deal with all this, but that's also why I'm a little bit frantic, and I can't imagine doing this in the middle of any other class besides you guys, because you really have held it together for me. So you're helping me hold it together. But yeah, this is like basically my last day. Or I said Brooklyn, I mean New York. I mean, I live in Brooklyn, but New York City. We're leaving New York City. Anyway, yeah, okay. Yeah, you can. Actually, we're going to Maine. I mean, where the white people at? Not for that reason. But we're going to Maine because it's like a COVID escape and other things like that. And again, like a lot of people in my life don't even know that, but it's happening. We might never come back. I don't know. And I was born in Brooklyn and I've lived in Brooklyn a lot of my life. So this is like a big deal. Anyway, right. Thank you very much. I don't even know why I'm telling you guys this, except it's like heavily on my mind. And like, that's what I'm in the middle of. So maybe I'm asking for a little consideration or space in the next few days. Like definitely if you have issues with grading or whatever, text me, but also maybe give me a little space to respond because I'll be in crazy land, even more than usual. Okay, but thank you for your consideration. And I'm really glad that you guys are the class that I mean, I'll continue teaching remotely, but I will sort of sentimentally remember you as my last Brooklyn experience. Thank you very much. I totally appreciate it. All right, I don't know why I'm talking about this, but that just shows you how personally I feel about you people. And I guess that I'm trying to transit. Okay, so physics. Oh, thank you. I totally appreciate it. Thank you. Okay. Thank you very much. I totally appreciate it. I don't even know why I'm stalling. I'm probably like nervous about starting this physics. Okay. I'm just taking a deep breath. All right, I'm going to start some physics now. I'm going to write some equations on the next page that are my focus for today. It's going to take me a while to explain them. I'm going to spend the whole time explaining them in a way, but I'm going to write them first so you can see where this is. You've never seen them before, or I mean, you maybe have seen them before, but you've never seen them in this class. You don't have to memorize them or anything like that. I'm going to spend the next 2.5 hours sort of trying to unpack the content of these equations to make a point to you. And I'm going to write them first, almost as a reminder to myself, and so that you can see where we're going to be going. But it will be maybe a little bit back and forth. But here's what today is about. Oh, okay. I'll tell you just in case. Okay. Now, again, I'm not expecting you to memorize this. I'm not expecting you to solve problems with these. I'm going to try to explain these in English. They're just super important. I'm going to try to, and they're a super important package. Some of you might recognize them. You've even maybe seen them on neckties and t-shirts, like for real. Or you might see them in a slightly different form. So the goal of the next 2.5 hours is for me to explain these 4 equations to you, again, knowing that you've not seen them before. And again, knowing I'm not testing you on the details of them or how to solve problems with them or anything like that. I want you to know what they mean in English, and that's really what all the true false things are ultimately about. Okay. So it's like the focus. So this is like the table of contents for today, or the punchline of today, or something like that. Okay. And I'm going to turn the page in a minute, but I'll probably flip back and forth to this page many times. These 4 equations are known respectively as Gauss's law for electrostatic fields or electrostatic flux, Gauss's law for magnetostatic fields or magnetostatic flux or magnetism. I'm going to explain that. But the first law is about electricity. The second law is about magnetism, which we haven't said anything about. I'm going to say a lot about it today. The third law is called Ampere's law. It's also for magnetism. The fourth law is called Faraday's Law, and it's about electromagnetism. Okay. Again, just try to follow with me. Now there's a lot of there's some symbols in there and you recognize. Like you might notice that yesterday I made a big point about talking about integrals, particularly integrals of dot products of vectors, right? I mean, there was a reason that I kind of like got really into that yesterday. You'll also notice that yesterday I talked about integrals with circles around them, closed integrals. All of these equations have closed integrals in them, not coincidentally. All four of these equations are statements about closed integrals of one kind or another. Now, the last two are integrals, closed integrals of exactly the form that we said yesterday. They are a closed circle integral with a dot product inside. So the second pair of equations here, the last two, which I'll talk about ultimately, are both what are known as closed path integrals.
So what does that say next to Q in the equation?
Sorry, wait. Oh,
In the parentheses?
Yeah. I'm sorry. Great question. It says, so in the top equation and the third equation, I'll try to make that neater. It says parentheses ENC. That's that's totally unreadable. And I'm going to explain that, but yeah, that says ENC. And ENC stands for enclosed. I'm going to talk about that, but right.
Thank you.
Oh, thank you. Good point. So I made a big point yesterday about okay, thank you, direct chat person. Totally, thank you. Okay. So yeah, that says, yeah, okay, and right. Yes, okay. So yes, good point, Antonio, and I was about to say that, but yes. So all of these are closed integrals, all four of them. The first two happen to be double. They have to be closed double integrals. I mean, I know this is very exotic and everything. What does a double integral mean? It means an integral of an integral, kind of like a second derivative, but specifically, it means a sum of a sum. It means ultimately like if an integral is adding up a bunch of things, or more particularly if an integral, and I was trying to say this yesterday, if an integral means like walking in a line and adding a bunch of things in that line, like walking a little bit of displacement, multiplying by the force, right? And again, I'm still recognizing, even on the last day of class, I understand that many of us are still fuzzy about integrals. I'm going to ask you, and I've been there, believe me. I mean, I spent half of my college physics major feeling very insecure about integrals. I don't want anybody to think for a minute that I just think they're like obvious or something. However, what I also don't want anybody to do, even on the last day of class, what I don't want you to do is just see the word integral and be like, forget it, I don't get integrals. I'm just like not going to pay attention until he says something else. Like, no, the way to ultimately understand integrals is to keep listening as people are talking about integrals and keep trying to get them a little bit more. And that's what they are about. In fact, what an integral is it's a process where you walk a little bit along a line. Like you can think of it as walking along the x-axis of some graph, if you like. You walk a little bit along a line, you think about where you're walking. Like it could be a little bit of x-axis, could be a little bit of line in a wire, could be a little bit of line like on a pathway where you're pushing a box, whatever. You walk a little bit, and then you take that length that you walked and you multiply it by something. You always multiply by something. In the case of work, you walk a little bit of a line, a little bit of displacement, and you multiply that amount of walk by an amount of force. And you take that little product, that little multiplication, like you multiply some amount of force times some amount of displacement, and you throw it in a bag in your mind. You throw it into a bag, and then you walk a little bit more. You take that next step that you walked, multiply that amount of step, like that amount of meters, by an amount of force measured in newtons, and you throw that in your bag. Then you walk a little bit more, multiply again, throw it in your bag, and you keep walking until you get to the end of the line. You add up everything that's in your bag. That's what an integral is. And I'm not joking. It is that simple in a way, if that made any sense. An integral is always a sum of lots and lots of little products. The thing that makes it fancy, and this is to go back to what Antonio asked a second ago, ultimately, but just to remind everybody what an integral is, whether you think you still don't understand them, which I have sympathy for, or you think you've been doing them for a while and you're not worried about them, then think deeply about what one is so you can apply to all this. An integral is always a continuous sum. The only thing that makes it fancy, the thing that makes it calculus, the thing that makes it hard, and excuse me, I should say an integral is always a continuous sum of products. It always is. That's why there's always like a little d something term in an integral. It's not just for bookkeeping or for math rules. What's always happening when you do an integral is you take something and you multiply by a little bit of something else. And then you do that again, and then you do that again, and then you do that again, and you add them all up and you get the big total, and that's your integral. The thing that makes it hard or interesting or exotic or whatever is that it's a continuous sum, meaning that every little step you take in the line along which you're integrating is always an infinitesimal step, like by design. Because we're always, whenever we do an integral, the purpose of why we're doing it is that we're trying to add up a bunch of things or a bunch of products for which one of the terms, like say force, is continuously changing, like not changing in chunks, not like 3 newtons of force for this step, and then 5 newtons of force for that step, and then 7 newtons of force for that step. Like if we had something like that, we could just literally add them up. We wouldn't need all this fanciness. But an integral is always a sum like that we perform when we're looking at some kind of quantity that's changing all the time without breaks. Therefore, we have to add up continuously. Like that means, like, what does continuous really mean? It means infinitely divisibly, right? Like in other words, we're thinking an integral is something you always do over something that's more not like grains of sand, but more like water, if you know what I'm saying. Like that's an analogy. But so anyway, an integral is always a continuous sum of products along some line, even if that line is just like an x-axis of a graph. That's what an integral is. A double integral, now to answer Antonio's question and to point out what I'm doing here, a double integral is like if you do that and then you do it again. In other words, if you integrate along some axis and then you integrate along another axis and get a two-dimensional quantity. A double integral is integrating rather than over a line, ultimately over an area. A single integral is a one-dimensional concept, and a double integral is a two-dimensional concept. And two of these equations that I'm going to talk about today actually are two-dimensional integrals or two-dimensional continuous sums. They're sums over areas rather than over lines. So, I mean, good observation on Antonio's part. And I'm going to explain that more. But just as an overview of what we're talking about today, yeah, I'm going to explain to you two important realizations about nature that are two of which are, excuse me, I'm going to explain to you 4 realizations about nature that have different names. All of them happen to be closed integrals of some kind or another. 2 of them are actually two-dimensional closed integrals. This is why I spent some time yesterday talking about closed integrals. Now, and closed, remember, closed means like round trip. Integral still means that you walk along some line from somewhere to somewhere else. If it's a definite integral, then you know where you're walking from and you know where you're walking to. If it's an indefinite integral, then you're just being more abstract. You're just saying like, okay, like, let's just do this. I don't even know what the endpoints are. Let's just like do this process in general for any endpoints, but there's always endpoints to an integral. A closed integral means you walk from some endpoint, some boundary somewhere, and then you come back to that boundary, right? That's what a closed integral means. And I'll explain what that means in the case of area soon. But so on the left side of all these equations that we're going to talk about today, they are all closed integrals of dot products. They're all kind of like the work integral. That's like why I reminded you of it yesterday. Just that 2 of these are two-dimensional. But the other thing is you'll see in 2 out of 4 of these equations on the left-hand side, like don't even worry about the right-hand side for the minute. On the left-hand side, in 2 of the equations, there's an E, capital E. I want to remind you that capital E stands for electrostatic field. These are field equations. We're ending the semester on some important realizations about how fields work in the world. Again, now fields are hugely important and hugely exciting, and they're part of this course. I'm still, for those of you who are still paying attention, and I appreciate it, I'm still not assuming that when I say the word field, you're like, oh yeah, field. Oh yeah, I'm totally comfortable with fields. Like I'm down with fields. Like some of you might be, and that's cool. Although I would also caution those of you, if you're too comfortable with fields, you might not have thought of them quite enough yet, because I love fields, but I'm not totally comfortable with them. Like, they are deep concepts. They're always worth thinking about. But for those of you who are like, hey, every time he says fields, I tune out. Every time he says fields, I'm like, whatever. I'm here to say again, like, yeah, it's a new concept. You can get fields as long as you're honest enough with yourself to say, like, I don't totally get fields yet. I'm here to try to help in these last 2 hours. It's like anything else in life. Like, first we introduce something, then we start talking about it. And in a way, the more we talk about it, the more we might feel introduced to it. Okay, so again, I'm just asking everybody to bear with me. I'm not asking you to assume that we've already locked and stocked the field notion and we're done with it. I'm asking you to assume that we've introduced it, that you have some idea in your mind, and I'm going to try to give you more and more idea of what fields are, specifically the electrostatic field, okay, which is what E stands for. I'm going to say more about it today, a lot about it. E stands for electrostatic field. You might want to write that down or something. And B, I'm going to tell you right now, even though I haven't said B, some of you might know, capital B, strangely, stands for magnetostatic field or magnetic field. Haven't said anything about that yet. Going to talk about it today. But just so you can even read these equations or translate or whatever, or for the rest of your life, capital E, whenever you see it in a physics context, stands for electrostatic field. It's like the gravitational field, but it's like for electricity. And capital B from here on in stands for magnetostatic field. I will get into that like shortly, but just and S, lowercase s, if I'm translating the left sides of these, S, lowercase s, stands for surface, as in area. So like a dot ds, if you see that in the top two equations, a dot ds, ds stands for like an infinitesimal section of area, an infinitesimally small little square. Sorry. Great question in the direct chat. And we do want to maybe be a little bit careful about this, but these are great questions so far. In the direct chat, there's a quick question about, is field the same thing as flux? Great question. I haven't actually really used the word flux yet, I don't think, in this class, but I totally am going to today. Field and flux are not exactly the same thing. I'm going to explain what flux is today. In fact, what flux is field through an area. That's what flux is. Now, I have to backtrack again for all of us who are still not totally comfortable with what field is, but no, field and flux are very, very related, but they're not actually exactly the same thing. Oh, I see why you're asking, because it's in the multiple choice. Okay, or it's in the true false. It's fine. I'm going to define more specifically, but flux actually means field through an area. And ds, or like S in these equations, stands for surface, as in area. So, and L stands for length. Okay, L, like lowercase l, in the last two equations, and I know I'm jumping around, but we're all hopefully looking at the same page here. In the last two equations, L stands for length, like infinite. So dl is an infinitesimal little bit of length, like a little displacement vector. That's what dl with an arrow over it would be, a little displacement vector. So by the way, dl in the last two equations means exactly the same as dx would mean. If you're comfortable with dx, as in f dot dx is work, right? If you're comfortable with dx or even dr, if you've ever seen that in another class or something, dl is exactly the same thing. I mean, there's different reasons why we use different things in different contexts, but it just means infinitesimal length, or in other words, infinitesimal displacement vector. Okay, that's what dl means in the last two equations. What ds means in the first two equations is an infinitesimal bit of surface or an infinitesimal bit of area. In other words, technically, what ds actually is like a little bit is a dx times a dy. So a double integral really is like e dot dx times like e dot dy with the e factored out. Okay, if that helps or not. So ds is just, if dl is a little infinitesimal line segment with direction, then ds is an infinitesimal line times another line, an area segment. Okay, now again, I'm not pretending that these equations are clear yet, but I am trying to give you piece by piece what the equations are referring to, so that we can put the pieces together in these 2.5 hours. So what I do think in my mind is that, and hopefully you're taking notes. Like, I don't want to like cloud up this whole page or make it all too confusing, but hopefully if you're following me, you now at least have like a little dictionary in front of you of what all the symbols on the left-hand side mean. I'll say it one more time, like An integral symbol with a circle means a closed integral, which means an integral from someplace back to that very place. Okay, that's what a closed integral means. And if it's a double integral, that means a closed area. Maybe I should define that in a second. ds means infinitesimal bit of surface or infinitesimal bit of area. So it's not a coincidence that the two double integrals have ds's in them rather than dl's. Like, that's totally on purpose. It's almost saying the same thing. Those are two-dimensional integrals, the top two. The bottom two are single dimensional integrals. Capital E stands for electrostatic field. Capital B stands for magnetostatic field, magnetic field. And in each one of those four equations, what you have inside the integral is a dot product of two vectors. In other words, a registration, a measurement of how a scalar product of the vectors, a product of the vectors that returns a value that is a pure number that shows you not only how big the two vectors are, but how parallel they are with each other. Okay, that's the left-hand side. Now on the right-hand side, just to continue to define notation and whatnot, and also to answer like Juanita's good observation, good question. On the right-hand side of the top equation, it says Q parentheses ENC over epsilon naught. Now the epsilon naught in the I'm going out of order, bear with me. The epsilon naught in the denominator, that top thing, is the constant that I gave you like a week ago. It's called the permittivity constant. It's 8.85 times 10 to the negative 12 Coulomb squared per newtons per meter squared, whatever. It's a tiny, tiny number. You certainly don't have to memorize it. It's technically called the permittivity of free space. But what it is part of the constant in that whole Coulomb law, in that whole the law for the electrostatic interaction between any 2 point charges, right? So epsilon naught is just a constant. It's a fundamental constant. It's just a number that's never changes throughout the whole universe. It's like Planck's constant or something like that. Again, you certainly don't have to memorize it, but how does it, like, what's the point of it? It's much like the capital G in GMM over R squared in the gravitational force equation, right? Like, it's just a constant that goes into the equation that shows us how strongly 2 point charges pull or push on each other through empty space. Okay, so that's what the epsilon naught is. It's a constant. And it wouldn't even have to be there at all if we were willing to measure in different units. It's just to make our units stay metric, honestly. So like, don't overthink it. The lowercase q in the numerator of the first equation stands for charge. Okay, like as in KQQ over R squared, as in Coulomb's law, as in, okay, so Q stands for an amount of net charge, an amount of extra protons that you have in some region of space, or an amount of extra electrons. If it could be negative or positive. That's what Q stands for. ENC stands for enclosed. I'm going to get into what I mean by that shortly, but it's not a coincidence that the left side of the equation says is a closed integral of some kind, and then the right side of the equation is talking about something enclosed. It's talking about the amount of charge that's enclosed within a certain area. Within a certain volume. I'm going to get into that, but that ENC stands for enclosed. Okay, then the next equation, zero means literally zero. Then the next equation after that says mu naught. You might not have been able to read that actually. I mean, but that's a symbol I've never used yet. It's mu naught times capital I parentheses enclosed. Now mu naught is another constant. Okay, it's universal, fundamental, natural constant. Technically, it's known as the permeability of free space, whereas epsilon naught is the permittivity of free space. Mu naught is the permeability of free space. And mu naught is also a very small number. It happens to be, oh my God, I always get this wrong. It happens to be 1.27 times 10 to the negative 6 henries per meter. What is it? What it is a constant that figures into a fundamental equation that tells us about the magnetic attraction or repulsion between any two magnetism causing objects. I'm going to get into that. But mu naught is just a fundamental constant. If you sort of have any picture in your mind at all of what epsilon naught, so it's like this. Again, I almost should turn the page and write this down, but I'm worried about doing that. If in your mind you sort of understand what big G is for gravity, like big G is just a constant that holds together the gravity equation and it just scales it appropriately to the units of the metric system, then what big G is to gravity, epsilon naught is to electricity, and mu naught is to magnetism. They're just the three constants that just scale things appropriately to make our units work out when we look at fundamental interactions in the universe. Again, I'll get back to magnetism, but that's all mu naught is, just a constant. You could literally ignore it if we weren't insisting on using the metric system. Then capital I, so I'm on the third equation now, right? Capital I stands for current, like electrical current, like you've been dealing with in the lab. I'm almost tempted to turn the page, but I'm not going to. Capital I means current, like you've been dealing with in the lab. What is a current? A current is a flow of net electrical charges, right? That's what a current is. Technically, maybe I'm tempted to write this. Yeah, I'm not going to write it. Current is flow of charge, right? I'm so tempted. I'm not going to write it. Current is flow of charge. It's dq dt, technically, right? Like current is a flow, meaning it's when you count current, when you have an ammeter that you put in a circuit somewhere and it's counting saying, oh, it's 3 milliamps of current there, or it's 7 milliamps of current over there, or whatever. What is it that it's doing? It's measuring or counting how much charge is rushing by you in a certain amount of time. It's not just counting number of charges sitting around. That would be just net charge. That would be Q. And it's not counting how fast a given charge is moving. That would be velocity. That would be the velocity of that charge. What it's doing is counting the number of charges that rush by you in a unit of time. Like if you were to stand on the wire and count, it's like standing on the highway and counting cars as they rush by. If you were to do that, if you're like, oh my God, 13 cars pass by every minute, like look how trafficy things are, you'd be counting the flow of cars. You wouldn't be counting cars in a pile, and you wouldn't be looking at the speed of any given car. You'd be counting cars that rush by, the flow of cars. That's what current is. Technically speaking, it's dq dt, the derivative of charge with respect to time, like for a given location. That's what I stands for. So I'm going to remind you, in fact, something I said. So I really want to write this down, but I really won't. But you really should. I, as in from the lab, as for the rest of your life, electrical current. I mean, this is a very practical thing. It comes up in life all the time. What it really is dq over dt. It's derivative of charge per time. It's like that straightforward. It's the fundamental time derivative of charge. dq, like here's where your calculus all comes together. Current is dq dt. Voltage, which you deal with in the lab all the time. I tried to say this yesterday and I know it got rushed at the end. What voltage is the integral of electric field with respect to length. It's integral of E dot dx or dr or dl, however you want to say it. Current is the derivative of charge. Voltage is the integral of electrical field. Now, again, I know that some of you might not be totally comfortable with what field is yet, and I'm going to go back to that, and you still might not be totally comfortable with integral. But if nothing else, take this last day of class as a plea for how like the physical world and calculus really do come together in the end. Calculus is not just like an exercise. Like, I mean, if there's anything practical about physics for most people in most of their practical lives, it's electricity. Like throughout their house, like I'm not saying everybody knows all the physics or the math of electricity, but people use electricity all the time. And as you know, tons of people get paid a lot of money to fix electrical things in your house, whether they care about the physics or not. And anybody who's dealing with electricity at all, ever, is dealing with three basic things all the time: voltage, current, resistance. What I just want to tell you right now is current is the derivative of charge of, current is the derivative of electrical charge. I'll say it even better. Current is the time derivative of electrical charge. Voltage is the space integral of electrical field. It is that straightforward. Like it all, anyway. So capital I, but we'll get back to that. But capital I in the third equation means electrical current. And then it has a parentheses after it, as Juanita noticed before, or she noticed the other one, but it has a parentheses that says, again, enclosed, just like in the top equation. I have to get back to that. I will explain that, but just to translate these symbols, the third equation says, in effect, the closed path integral of magnetic field equals some constant times the current enclosed. I have to explain what I mean by that, but just so you know, it's saying current enclosed, just like the top equation is saying charge enclosed. If nothing else, again, even if what I'm saying is like 60% of it is sort of making sense, but 40% is just like jibber jabber, just notice the rhythm of what I'm saying. Like, honestly, notice there's something about these equations that's all kind of like in a pattern. Like all the left side, like there's two equations about electrostatic field. There's two equations about magnetostatic field. There's two equations that are closed path integrals. There's two equations that are closed surface integrals. That is not a coincidence. This is a tidy package that ultimately tells us how space and time work. Like, and I'm just trying to sort of build this in layers for you. But and then the right side, you know, has this idea of enclosed comes up twice, not coincidentally. Now, finally, in the very, very last equation, which looks very strange at the moment, I'm sure, what's happening on the right side is a bunch of symbols, but you know all those symbols now. Like the right side has a negative sign, the right side of the last equation, what's called Faraday's law, has a negative sign, then it has ddt, time derivative of double integral of magnetic field with respect to ds. Like ds still means infinitesimal bit of surface. It's an or area, since it's an infinitesimal bit of area, that's a double integral there. In other words, the right side of the very last equation, if you're looking at it, and again, we're just trying to layer this, but if you're looking at the right side of the very last equation, you should see that it actually kind of looks a lot like the left side of the second equation, not coincidentally. It looks a lot like. They're both about magnetic field through an area, or in fact, what's ultimately technically called magnetic flux, to go back to a question I got before. They're both very similar, but they are different. I mean, they're both about magnetic flux. The left side of the second equation and the right side of the fourth equation are both about magnetic flux. However, you'll notice that in the second equation on the left, I did put a circle. And yet on the right side of the last equation, I didn't put a circle. That's not a typo. That's not a mistake. That's actually on purpose. In other words, in the left side of the second equation, we're talking about the magnetic field through a closed area, whereas very deliberately, maybe mysteriously, I'm saying on the right side of the last equation, I'm talking about magnetic field through an open area. I will explain that, but just note that's on purpose. And then even weirder, on the right side of the bottom equation, you know, to the left of this double integral of area, it says time derivative. Now, that may seem strange to you. Like if you've been following calculus at all for 2 years, or, you know, trying, even if you're not, you might be like, wait, I thought an integral was a derivative backwards. Like, wait, I thought the fundamental, you might think something like, I thought when you do an integral, you undo a derivative, or vice versa. Or I thought there was something about the fundamental calculus that said that like integrals were antiderivatives. So what the heck is Yavr about like taking the derivative of an integral in the last equation? Like that seems like a mess. Well, it is a little messy, but just to warn you, because we're going to try to put this, we're trying to put this all thing together to understand the universe. That last equation, that right side, says take the derivative with respect to time of some integral that's with respect to space. Like in other words, the independent variables are not the same in that right part of that last equation. I'm not saying it's a mistake. I'm not saying it's a contradiction. What I'm saying is it's not a contradiction, and it's not redundant or undoing itself. It's actually saying add up a bunch of things throughout space and then ask how they're changing in relation to time. That's what it's technically, it's saying what's the time rate of change of some surface integral. It's a mouthful. Again, I'm not saying just because I just said that, you should be like, oh yeah, that makes total sense. But I am saying, please at least understand it's not a mistake. And maybe it might spark your curiosity a little bit. Like the last part of the last equation is asking us to look at the rate at which something in the area of space changes as a function of time. Okay, now all I've done for the last God knows how many minutes, all I've done is like define all the symbols in these four equations. My goal for today and for your final exam is to actually get you to see what these equations are saying by the end. But right now, what I've just done hopefully is at least giving you a lexicon of the terms in them. Okay, they are ultimately, what they are is the shape or the character. What they are is a complete description, an almost complete description. It's a package of equations that ultimately tells us sort of the shape and behavior of the electric fields and magnetic fields in space. That's what, and time. They're trying to say like how electric fields and magnetic fields behave in space and time. And once you really do see the package, what is revealed is the nature of space and time in a kind of a big way. So they're like worth understanding as a package. Again, so now I'm going to like try to unpack them and tell you what they mean. Again, there's no assumption that you've seen them before. There's no assumption that you have to solve a million problems with them. I just want to like translate them for you and have you see how it puts the course together, hopefully. Okay. You've been very patient so far. I'm going to take a breath. We're going to flip the page in a moment, but again, it's all about these four. So, be prepared to, and you may or may not have noticed, well, you may soon start seeing that most of the true false statements in the final exam actually are about these in one way or another. Like, I don't know that you could answer them all yet, but hopefully you're starting to see that they are English statements about these equations. Okay. Now I want to back up and really start explaining fields to you again. Like, these are observation or recognitions that we have about fields, but I want to give you a clearer picture of what fields are in order to do this. Yeah, so let's do that.
Professor, what does that say after powerful?
Oh, sorry. Yeah, good question. Statements. Sorry. Or it's supposed to say. Sorry. Okay. The key on this page is the black part at the bottom, which is probably written too small. I should probably write it again on the next page, maybe in a minute, because it's like super important. But well, I'll just read the page first, but then here's what I'm trying. So the four previous equations make powerful statements about electrostatic and magnetostatic fields. But what again are fields? Like, that's the issue, right? I mean, if you can really if we can all get our minds around fields, then we really have gotten our mind around something super important in physics and in the universe. So let me try to remind you what fields are. In a way, a field is a very simple, in a way, certainly mathematically, a field can be understood as a very simple concept. I'm going to remind you in the context of electricity here, because it's like kind of our focus. But anything I say about electricity, you can always bring back to gravity in your mind if gravity is clear to you. So like remember, with gravity, any 2-point masses automatically and always pull on each other through empty space with a force measured in newtons that we call the gravitational force, right? And it's always, and the strength of that force is always the product of the size of one mass times the size of the other mass divided by the distance between them squared, right? That's like the way it is. And it's sort of makes sense. Like the bigger each mass is, the more it pulls, and the farther away they are, the less they pull, right? Now that's gravity. Now, same thing happens with charges, with protons and electrons pulling on each other, or protons and protons pushing on each other. Same thing of they just automatically pull or push on each other without touching, without trying to, without doing anything. Just if a charge exists in space, it will automatically pull or push on any other charge in space just because they are charges and because the universe seems to work that way, right? And just like gravity, the bigger one charge is, or the bigger the other, the more they'll pull or push. And the farther they are from each other squared, the less they'll pull or push. Just exactly the same math as gravity. And just like with gravity, there's a big constant before, at the front of the equation that I'm putting in parentheses. And remember from the beginning of the semester, like a bunch of constants together is a constant. So it doesn't matter how you write it, but there's a big constant. Don't get bogged down in it, or don't worry about it, but it is 1/4 pi epsilon naught. And so the force F sub E, the force vector that any 1-point charge exerts on any other point charge, is given by that expression. And it has vector symbols in it because it is a vector. Like force does have magnitude and direction. And we're using that unit vector to express like the idea that, okay, the force, the electrostatic force exerted by one proton on some electron points in the direction of the line that you could draw in your mind going from one charge to the other charge. Like that, like don't get intimidated by that R hat. I know it's new to many of you. It bothered me for years, but just that R hat is saying this is a vector. It has direction, and specifically it's pointing in the direction of R, which means the displacement from one object to the other. So it's like a funny way of writing things that might be new to some of you, but it just is saying that force not only has magnitude as given by that whole multiplication of numbers, but also has direction. It's a vector. Okay, now that's what the force, the electrostatic force exerted by one charge onto another charge is. That's what that F sub E says over there. The F, the force, it's measured in newtons. It's an interaction between two objects. We have many kinds of forces in life. We have friction force, normal force, tension force, all kinds of spring force, all kinds of forces in life. Forces are always interactions between objects, pulls or pushes between objects. The thing about the electrostatic force is that it's unusual. It's not unique, but it's unusual. It's different from the normal force or the tension force or the spring force or the friction force. If I didn't say, it's different in that it seems to happen automatically through empty space without any attempt, without any trying, without any touching, right? Just if a proton is just sitting around, it will automatically be pulling or pushing through any other electron or proton that's just sitting around anywhere in space, right? That's kind of weird. In fact, it's so weird that there's no reason to believe it at all, except that we see it happen all the time. And it's so weird that it's like nothing we've ever seen before, except the other things like it that we've seen, like gravity, right? Like remember, so I'm saying the electrostatic force, it turns out, is a fundamental force like gravity. They're both fundamental. This goes back to like a week ago, and this is like questions that like Avery Yeller was asking in class and other people and Caleb, that electrostatics, which I'm talking about right now, the electrostatic force is, first of all, it's called electrostatic force because it presumes there's no necessity of motion whatsoever. Electrostatic force between charges, it doesn't mean the charges can't be moving. It means they don't have to be moving. It means just like with the gravitational force, which could have been called the gravitational static force. I mean, we could have called it that. The point about both of them is that if you just exist as a point of mass or as a point of charge, you automatically pull or push any and every other point of mass or point of charge any and everywhere through the universe. And you do it without trying to do anything, without touching, without reaching out and grabbing, without having anything in between you to mediate or translate or transmit the force, evidently anything material between you. So these forces just happen through empty space. That's really weird. It's really so weird that we wouldn't believe in them at all, except that we see them happening all the time. Like things just automatically get pulled to the earth, right? And for the longest time, people thought that was because something was special about the earth that it pulled things toward it. And they thought something else was special about the earth. They thought the earth sat still at the center of the universe. Eventually, people realized, Galileo realized it is in heaven as it is on earth. Like what's going on in the skies is no different from what's going on here on earth. Earth isn't special. It's just a freaking rock zooming through the heavens, and whatever the laws of motion are that govern what's going on up there apparently are the same laws that govern what's going on down here. And Galileo and others realize the earth isn't special. The earth doesn't have a special property of pulling things towards it. Everything apparently has this special property of pulling everything towards everything. I mean, it's special in that it's fascinating, but it's not unique. It's the nature of existence. That everything pulls on everything else, gravitation. Every point of mass in the universe automatically pulls on every other point of mass, and every point of charge automatically pulls on every other point of charge in the universe. Now that's already weird enough. I mean, that's already, wait a second. I'm just looking at the chat. Yes, totally yes. And I'm going to get to that, but yes, good question. Direct chat person answers totally yes. And I'm about to say, but oh, I see what he's smart. He's looking at so at least one person here is totally trying to follow this and totally trying to see match what I'm saying to the true false questions. Good. I mean, that's why that is not cheap. Someone just knocked off one of the questions by paying attention to what I'm saying. That's good. I mean, I won't say any more, but good. The answer is yes. But so what I'm trying to say right now is it takes two objects to exert a force on each other, but some objects exert forces automatically through the universe. That's already strange enough, but then when you get quantitative about it, okay, and this really bothered Newton, this drove Newton crazy, the one who discovered this, he couldn't believe it himself, that if we really believe that the amount that a proton pulls on an electron actually depends on how far away the two objects are, right? R squared, the R squared in the denominator. If it actually depends on how far away they are, that means that when one of the two objects changes its location, gets closer to the other, for example, then the other will start exerting a different force. That means that the information of an object's whereabouts is somehow getting transmitted through empty space all the time to other objects, that every object in the universe in a way knows where every other object is in the universe. I mean, that's what this means, honestly. Like if we believe in action at a distance, if we believe in forces transmitting through empty space, it means that somehow quantitative information is being held in empty space and being conveyed through empty space from one object to another all the time. And by object, I mean either point mass right now and or point charge. And that's weird. I'm not telling you, I'm not saying duh. I'm saying think about that. If you think about it too much, you'll maybe go crazy, but like Newton did. But if you don't think about it at all, you're crazy. Like that is a weird idea. We do not think it should be logical. We just think it, as scientists, that it appears to be happening. So we say, well, if the sun can know where the earth is at all times, which apparently it does, if a proton can know where an electron is at all times, which apparently it does, or if, better yet, if a proton can know whether there's 2 electrons nearby it or 3 or 7, right? And apparently it does because it adjusts its pull or push accordingly, then then somehow the information must exist in the space between the proton and the electron, somehow. And somehow this information must get across. When the information changes, the change in the information must be transmitted. That mechanism we call a field. Okay, a field is an abstract idea. A field is the body or the medium or the mechanism or the agent, the intermediary that holds and conveys quantitative information from one object to another through empty space. The field exists in space to hold and transmit this information between objects. To put more specifically then, as someone just asked in the private chat, like what I'm saying is, if you understand, if a force is something that one object does to another, then a field is something that one object does to space before the second object even ever comes along. Like mathematically, the field idea is very simple. Mathematically, the field is literally just force per charge. It's just force divided by charge. You notice, look at the two equations that I have here. It's not a coincidence. I know they're all crammed and small at the bottom, but it's not a coincidence or an accident that the force equation and the field equation for electrical point charges look identical to each other. Only difference is that the force equation is two charges written in the numerator, Q1 and Q2. And the field equation has one charge written in the numerator, just Q. That's the only distinction between the two. A force is something one object, one point charge does to another point charge. A field is something that one point charge does to space. Okay, put one last final way. We used to believe that the sun pulls the earth through a force measured in newtons. We used to believe that a proton pulls an electron via a force measured in newtons. But once we started realizing, wait a minute, this force is happening in empty space. Like, it's not like the normal force or the tension force or the friction force or the spring force. It's not happening for trying or for touching. It's happening in empty space. So we now say, okay, no, the proton doesn't pull the electron. The proton creates an electrical field all around it. It creates a field. It deposits its own information. It deposits the size of its charge of itself, the number of coulombs. It deposits its own location, sort of in the form of a vector. It deposits it into space everywhere. It tells space where it is. It puts that information in space. And then if a second charge ever comes along anywhere in space, then it's in the field of the first charge and gets pulled or pushed by that field. We no longer say a charge pulls or pushes another charge. We say a charge creates a field. Like we say a source charge creates a field everywhere throughout space. And a second charge, a test charge, if it's dumped in that field, experiences a force from that field. I create a field and the field pulls or pushes you, right? It's an intermediary. It's like a medium, like a wave. Okay, and it exists everywhere in space. And what it is, I'm going to start drawing on the next page, how you can think about a field is like a bunch of vectors that are everywhere in space. In fact, some people call it a vector field. You can think of, well, I'm going to draw it in a second, but you can think of a field as for every point in space that you imagine, like say the gravitational field of the sun. You can think of it as in every point of space that you imagine, there's a little arrow. They're pointing towards the sun of a certain length. And the farther, and all the arrows are always pointing towards the sun. I'm going to draw this in a second, but all the arrows are pointing towards the sun if we're talking about the gravitational field of the sun. But the farther away you get from the sun, the smaller the arrows are, because each arrow represents at that place how many newtons of force and in what direction, how many newtons of force would be exerted and in what direction they'd be exerted if 1 kilogram of mass, test mass, were to be placed at that location. So a field is just like a bunch of vectors everywhere you could think about it. Now, and I'm going to draw that in a minute, but let me again say, if you think this notion is at all weird, good, that means you're listening. If you think physicists are at all crazy for coming up with this, or like we're starting to believe in things that you're like, okay, if you say so, boss, like fine, there's arrows everywhere in space, good for you. If you're thinking anything like that, good, that means you're hearing me, because it is a weird idea. We are literally saying something exists in space that is not material, that is not tangible, that's not visible or fragrant or anything else. We are saying that everywhere in space, from every object that exists, there's this thing called a field, which is a bunch of vectors, a bunch of information. You can say that's weird. And let me say, and again, if you don't think it's weird at all, if you're just like, yeah, field, field, right? Okay, vectors everywhere in space. Then really, then I feel bad for you. If you're just like writing it down to get it right on the test or whatever you feel, then like I don't really, then I think you've turned off kind of an important critical part of your brain. There is part of what I'm saying that's very strange, almost maybe upsetting. Let me say 3 things about it before I start drawing it. 1, I know that. We know that. So you're not crazy if you think that. So maybe it's 4 things I want to say. 2, I'm not literally saying that there's arrows everywhere in space that are like drawn. Like I'm not saying that there's, when I say there's vectors everywhere in space, I do want you to know I'm not that crazy. I don't mean they're like made of ink or cardboard or something. Or if I even say there's numbers everywhere, if I shout at you, if I sing the note A to your ear and you hear the note A, I am saying that in some very important way, I've sent the number 440 to your brain. I'll stand by that to my grave. Like, I believe that if I sing the note, if I sing it right, I've sent 440 vibrations to your brain, and that 440 has undergone a lot of translations. Like it's 440 vibrations of a certain kind of material, then a different kind of material, then a different, but yet the 440 has stayed all the while. So if you hear the note A in your brain from something that I sang, I am saying I sent you a number. I mean, I sent you other things too, maybe, but I certainly didn't send you a bit of material. I didn't put an object in your brain, but I did put something in your brain if you heard it. And what I put was a number. But I don't mean a numeral. It's not like Sesame Street. I'm not saying that I sent you a cardboard like 440. In fact, like 440 is just the symbols that we use like in our language. Like obviously in other languages, they don't even use those symbols. They use it. So there's a big difference between a piece of information and the symbols that are material that we use to represent that information. Similarly, if I say there's vectors everywhere in space, I don't want you to think I'm that crazy. I'm not saying that there's cardboard arrows, or when I say that the sun knows where the earth is, I don't mean it knows like it's sitting there like planning its lunch around that knowledge, not that kind of knowledge, but I'm saying the information, like I'm saying the difference that makes a difference, or something that isn't matter, but matters. I'm like, if you believe in justice or love or anything else abstract that's not material, then you can believe in vectors. And vectors aren't material. They're our way of understanding something that's going on in the world. And I'm saying that is what exists everywhere. If there's a field created by a proton or a sun, then I'm saying you could think of it as vectors everywhere in space, meaning information, quantity and direction somehow is in space to be retrieved by other objects. Again, I'm going to draw in a minute to try to make it more, what I'm really trying to do, I'm not trying to, well, yes, I am, but what physicists are trying to do is recognize the existence of abstract things. Like again, in other courses, you recognize the existence of abstract things like love and justice. Here in physics, which is supposed to be super concrete, it's supposed to be about stuff moving through time and space. We're just saying as physicists that the more we look into time and space and motion, we see things moving that are not concrete, but we see them nonetheless. And what we're trying to do with all of our models and representations, vectors, math, field lines, we're just trying to put concrete pictures in our brain for these really abstract things. We still know they're abstract, right? But we're trying to have concrete predictive models that work for them. So the last thing I'm trying to say, so if nothing else, if you had to shut off right now, if the course ended right now, I'm asking you to believe in fields, or I'm certainly asking you to understand that fields are a big part of the universe and physics. You can choose not to believe in them. You can also choose not to believe in electrons because you've never actually held one in your hand and stuff. But ask yourself why if you choose not to believe in them, and also ask yourself what possibilities you might cut off for yourself if you choose not to believe in them, because you might as well also not believe in justice or love or something else. The last thing I want to say about, and once you do believe in fields, or once you start picturing fields as the information, what a field is the information of one bit of space. Sorry, what a field is the mechanism or medium. And again, maybe write this down. I'm going to start trying to draw it in a different way, but a field is the mechanism or medium by virtue of which one bit of space accesses information appertaining to any and every other bit of space. A field is the information of different parts of space, like being communicated from one part to the other. That's what a field is. It's the information container. There is a lot of information in space, and the field is the ever-pervasive container for that information and transmitter. The last reason I want you to start, and if you just want to picture it mathematically, field is just force per object. If force is always measured in newtons, then field is measured in newtons per object. If it's a gravitational field, it's newtons per kilogram. If it's an electrostatic field, it's newtons per coulomb. All it is, whatever a force, so anytime we have an action at a distance force between two objects, the field is the thing that we picture as being associated with just one of those objects. I mean, it really is just the force concept dividing out one of the two objects. But the last reason to believe in it or picture it or use it is just remember, no matter what, whether you want to say there's a field there or not, there is the information there. Like no matter what you want to say, the earth is pulled towards the sun, or like objects are pulled toward the earth. And objects do get faster and faster as they fall toward earth. Like objects seem to respond in a way that does seem to indicate the location of that object compared to earth. So one way or another, the information is there. The field is just our word for that fact. You don't have to picture a field as red or blue or having arrows or not, but it's just a word for this phenomenon that goes on. That information seems to exist in and get transmitted through empty space. Okay, that's what the field notion is now. I'm going to start drawing them. 2:30. Okay. Yeah, okay, that's a good question. You're totally looking at the thing. Yeah, that's exactly what I'm going to do. Direct chat person, that's great. I totally see that you're following this in the true false, and everybody else could take a page out of this person's book. I won't mention the name, but he or she is totally right to do what he or she is doing. And well, I'll tell you right now, the question that's in the direct chat, I'm not going to mention names, but the question in the chat right now is how are electrostatic field lines different from electrostatic force vectors, if they are different? Very good question, because if you look at the true false final exam thing, you'll see that that distinction is made at various places. I'm going to discuss that right now. Good question. Okay. Okay. One way to picture fields, one way is what I said a second ago, as to picture a field as a bunch of vectors everywhere in space. Like if I put a positive point source somewhere in space, like space is empty, space is homogeneous and isotropic, like space is like the same everywhere, and it really is. That's an important property of space. It's just like it's sameness everywhere. But if I put like a proton, a point source, a positive source of charge, a positive point source of charge somewhere in space, right? Now, if I want to picture the field, the first way I can picture it is I can picture, like I was saying a second ago, I could picture that like for every point of space you look at, there's a little vector sitting there. And so I've drawn a bunch of vectors here surrounding the point source. I'm just drawing a few representative ones. Like in principle, there'd be vectors everywhere you looked, but I'm just sort of drawing the pattern of them because I can't draw infinitely, right? And they would go on forever. But the idea is that any point in space that you pick some point like in the upper right-hand corner, there's a vector there and it's pointing out and it has a certain length. What that vector represents is what would happen, what would be the push in newtons if I put a positive 1 coulomb of unit test charge there. Like what the field is like a what if. It's like a hypothetical. The field, remember, this point source creates this field before there's anything else in the universe. It's putting these vectors everywhere. And what the vectors answer the question is, what if there were a second object somewhere? What if there were a receiving charge, what we would call the test charge? And maybe you see now why we call it test, because it's like a test. Like if we were to put a positive 1, and you might want to write this down on a piece of paper if you're with me. Test charges are always assumed to be positive 1 unit of charge. Okay, just like a test mass would be 1 kilogram, because it's like unit. These are always assumed to be positive 1 coulomb of charge. So if I put a positive 1 coulomb of test charge up in the upper right-hand corner, first of all, I would assume that it would be, I would see that it'd be forced away from the positive source charge. It would be pushed up and to the right because positives repel, right? And it'd be pushed a certain amount, a certain newtons of charge, a certain number of newtons of force. It'd be pushed up and away from the source because it's repelled, and it'd be a certain amount. If I looked at a dot that's like higher up and farther away, there'd be a vector also pointing along that same radial line. Like I'd still be pushed in the direction away, but it'd be a smaller vector because KQQ over R squared. Like the farther away you are, the smaller the repulsion, the smaller the force vector, right? So all the arrows, all these vectors point radially out from the point source, but they get smaller and smaller as you get farther away. So they are vectors that represent what force per unit coulomb would occur if there were unit coulombs anywhere in space. Okay, that's a way to picture a field. And notice that would be the field from a positive point source, like a proton. If I wanted to look at the electrostatic field from a negative point source, which I totally could, like an electron, right? Then I'd have the same kind of picture, but all the arrows would point in now. They would all be pulling because we're still always assuming, this is why I asked you to write on the piece of paper, we're always assuming that the test charge of the recipient, the second object that would experience this field, we're always assuming that is positive 1 unit. Like, again, it's an assumption. It's why we call it test, because the field is what is created by one object. It doesn't need a second object to be there. What the field is what would happen force-wise to a second object if you're ever put in, right? So again, force is measured in newtons, field is measured in newtons per coulomb. And we're always assuming per 1 positive coulomb. So if you want to look at the field vectors that would exist from a negative point source, they would all pull in, because if we put any positive like little proton out there, it would get yanked into the electron like attraction. And again, the arrows get smaller and smaller as we get farther away. Okay, so now this again is answering direct chat person's question, or I'm getting to what these two things would be a way of picturing fields. These are called vector field diagrams. Perfectly legitimate, perfectly useful. People do it. It's one way, and they help you with all good. If you're beginning to picture that what a field is that's created by one object is a bunch of vectors everywhere in space, right? And really, mathematically, it's a vector valued function. It's really like a rule that I write down that says wherever you are in space, there's a vector that would represent the number of newtons per coulomb that you would experience if you were at that point in space. Okay, so these are vector ways of picturing the field. whatever is true of vectors would be true of the field. And again, we're not believing that there's literally like arrows in space, but we're believing that if we picture arrows in space, whatever the arrows would do is what space would do. It's a model, it's a scientific representation, right? Now, it's a good representation, it's totally accurate, it totally works, but it's very clumsy and annoying. It's like hard to draw. Like what I just drew was the field from just one point. It's like a big pain in the butt to draw all these arrows. So what comes along, I'm just looking at the time. Oh, okay. What we do instead, and again, this does relate to the true false, you'll start to see what physicists do instead, what a physicist named Michael Faraday, well, actually, he wasn't a physicist, he was a high school chemistry teacher in Scotland, actually genius. High school chemistry teacher developed this idea, and you may be familiar to you when you see in a second. He was a real heavy hitter. He was a great physicist, and he was really bad at math. Side note. Well, the point is he came up with this idea of drawing field lines, which I'm now going to do on the next page. And field lines are like vectors, but they're actually an easier, more natural, more smooth way of picturing fields. And we've adopted this as the standard. And Michael Faraday lived at the turn. He lived in the, I always get this. Michael Faraday lived in the middle of the 19th century, like in the, in the late 1700s, the early 18th century. And he came up. Why am I suddenly confused? And who cares? You don't care. Why do I care? Well, because I kind of worship him because he's kind of awesome. Anyway, he came up with this way of connecting all the vectors and thinking of it slightly differently, which we're going to do now. And then we're going to use for the next hour and a half and the rest of our lives. What he said is, it's too many arrows to draw. Let's just connect them all up. Let's connect them all up and do something instead called field lines. So I'm now going to draw the exact same situation, but I'm going to use lines instead of vectors, okay? Now, it doesn't look very different, right? It's like, what I just did was connect all the arrows together into like each of the arrows that were all along a radial line. I connected them all into one. Doesn't seem like a big deal. You'll see in a minute, it has huge advantages. It makes drawing diagrams of much more complicated situations a lot simpler. These are field lines, not vectors. What's the difference? The difference is I don't draw a separate vector at every single point. All vectors that are sort of parallel or pointing the same way, I connect into one big line. And these lines go off to infinity or come in from infinity. The difference here is that they're simpler to draw, okay, and they ultimately convey something different. But the point is that the vectors are connected. Oops, sorry. You can't read this. I don't want to get too direct. What that says, I mean, you can't read it, but it says all aligned vectors are connected now. All vectors that are aligned are connected. There's no longer a separate vector at each point in space. That's the key point here. In fact, the real key point here is in these line diagrams, and please write this down, field lines, these are electrical field lines, okay? By always, in the way that these are drawn, and please do write this down. I'm not going to get myself bogged, but please write down electrical field lines always start at a positive charge or come from infinity. I'll explain that in a second, but all electrical field lines start at a positive charge or come in from infinity. All negative, sorry. All electrical field lines either start at a positive charge or come in from infinity. All electrical field lines either end at a negative charge or go off to infinity. I'll say it one more time. Maybe you heard this in middle school, but all electrical field lines start at a positive charge or come in from infinity. All electrical field lines end at a negative charge or go off to infinity. Now you might say, wait, what other option is there? Or what the heck are you saying? Like, what do you mean go off to infinity or go end at a negative? What I'm saying when I say that is, unlike vectors, field lines never start or stop anywhere in empty space. These all field line diagrams are arrows that are just going on and on and on. Or coming on and on and on. They never start or stop unless you literally see a positive charge or a negative charge. Like so they can start at positives or they can end at negatives. Other than that, they never start or stop. Unlike those vectors, which are like starting and stopping everywhere in space. See, it's a big difference. It's just a drawing thing. We're just talking about drawings now, right? But this drawing, ultimately, once you get how to draw these things or how to read these drawings, they become the picture of how we literally do visualize and understand fields in space. We don't believe anybody's actually drawing lines with magic marker in space. But once you actually picture what these lines are doing on a piece of paper, they become our way of picturing what fields are doing in space. So the first thing to understand about these lines is all I did was I connected up all the vectors that would have been there, but I connected them all up so that I don't have any lines ever starting or stopping in space. They start at positives, they go to negatives, or they come in from ever and go off to ever, okay? Now, how do you read them or what are they saying? Well, just like, and again, please write this down now, or what I'm about to say, if you can. I mean, I'm just trying to be careful. If I start writing too much, I'll never get to where I'm going. But so I'm saying basically, I'm trying to describe to you right now how field lines work. They're like vectors in that, first of all, they're built from vectors. Second of all, they're like vectors in that they're a tool, they're a representation, they're a model, they're a way that we understand. They're just like graphs. Like, just like you have to spend all this time in math class and science classes, like understanding how to read graphs. And of course, everybody hates it for years while they're doing it. I hated graphs forever until I didn't. But if you've come this far in science, you know that at a certain point, you just got to deal with graphs because eventually, once you start knowing how to read a graph, that you're picturing reality when you picture a graph. You're picturing cause-effect relation, right? Once you get graphs, you understand that there's the simplest possible way to picture reality. They are not reality, but they're a tool for picturing reality, right? Same thing, field lines are like that. Or they're like free body diagrams too, if you're into free body diagrams. Field lines are the way we picture the reality of fields. So the first two things to know about them is what I just said, that field lines don't start and stop in space. They start at positives, go to negatives. Or I'm just going to close the window because I don't know if you can hear that, but there's like somebody like mowing a cow outside my. Sorry, I did not mean mowing a cow either. That's disgusting. I don't know why I said that. I'm sorry. Just to see if you're paying attention. Okay. But the other thing now about field lines, I want you to write this down. I'm not going to write it, but it's super important. And it's totally a true false question. I'm sure of it. Or maybe it covers two of them. Is that, well, I'll say it. With vectors, vectors are representations, right? A vector is an arrow. It represents a quantity. I do see a lot, by the way.
Can you repeat that, Professor?
Oh, I'm sorry. Yeah. I don't even know what I said. Oh yeah, a vector, and thank you for totally paying such close attention. I gotta say, some of the others, I do see that a lot of assignments are coming into the classroom while I'm talking now. Like, no offense, but like that might not be your best use of time right now. Those of you who are like submitting assignments to classroom right now while I'm talking, it's not necessarily the smartest move. Maybe it is. I guess it does mean you're here in front of your computer doing, anyway, whatever. Yes, I'm sorry, Juanita. I prefer what you're doing with this class time. Juanita just asked me to repeat what I said, but what I said was, oh, vector.
Yeah, you were saying that the vectors are representation, and then I didn't hear what you said after that.
Right, thank you. Okay, because, right, okay, a vector is a representation of a quantity with magnitude and direction. And so a vector is an arrow. The length of the arrow represents the size of a quantity, and the orientation of the arrow, like the tip tail, represents the direction of that quantity. Okay, I'm saying that as a reminder to everybody, as a reminder and for contrast, like whenever we draw these arrows on a paper, we don't believe that there's actually arrows in real life, but the arrows represent something. Every arrow, the bigger the arrow, the bigger the size. So like if it's a displacement arrow or a velocity arrow, the bigger the arrow, the larger the size of, say, the velocity, i.e. the larger the speed. And the orientation of the arrow, where the tip is, where the tail is, shows you the direction of the velocity. Okay, that's how vectors work. And that's why I had to make smaller and smaller ones of them on the back page when I drew a vector diagram. Now we're going to do field lines instead. Field lines are like vectors. So the first thing to write down is a vector represents magnitude and direction. The size of the vector arrow represents magnitude. The orientation of the vector arrow represents direction. That's vectors. Field lines also represent quantities with magnitude and direction, only they do it differently. If you look only, and here's totally one of the true false questions on the final is, yes, the orientation of a field line does represent direction, just like vectors. Like where the tip and the tail of the field line are going shows you the direction of the field. That is exactly like vectors. The orientation of the field line represents direction, just like the orientation of a vector represents direction. However, and this is totally a true false question. However, the size of a field line does not, like I'm totally giving away the answer. The size of a field line does not represent magnitude of quantity in the way that a vector does. So again, and I know I keep on saying it slightly differently, but what I'm trying to say is if you look back to this picture right here, each of those is a vector. The size of the vector shows you comparatively the size of the quantity. That's on purpose. That's the idea of vectors. Now we're shifting and going to a new representation, a new tool. Again, only for an hour and a half of today, but for the rest of our lives, we're going to a new concept, which is called a field line. And with a field line, the size of the line does not represent the magnitude of the quantity. It couldn't, because these lines are all necessarily like infinite, like they'll start at a positive and then they just go on forever. They all are the same size. We connected up a bunch of vectors on purpose to make our drawing simpler, right? So what you got to see is here, we have, that's why I'm saying they are like vectors in that they indicate direction, but the size of them does not indicate magnitude. Well, if I stop there, then field lines would be a bad idea. If they could only indicate direction and they didn't indicate magnitude, they would not be very useful to a physicist or to our purposes. If you're still with me, and I know that at least two people are, like I know Juanita is, and I know the person in the direct chat is, and I'm sure the rest of you are, I know. But what hopefully you're seeing is that we're now going to go to a representation that's easier, that's better, it's more powerful, it's easier to draw than vectors. But right at this moment, in terms of what I'm saying, we're not finished yet, because all I've said is how these things capture direction. It seems like they've lost something that vectors had. It seems like these lines don't show. Well, okay, that's great, direct chat person. That totally shows that you're paying attention, direct chat person, but jumping the gun slightly, like, so I'm going to read this out loud. It's not incorrectly. So the direct chat person just wrote, oh, so field lines don't show magnitude. It almost sounds like that's what I'm saying. What I'm saying is, based on what I've said so far, it doesn't seem like they do, because I haven't said how they do. And they certainly don't show magnitude in the way the vectors do. Certainly the size of a field line does not show magnitude. However, now here, so that person is paying attention, but here's why they still really, but however, there's a however. Field lines do show magnitude in a completely different way. And this is what you have to get used to from here on in for the next hour or whatever. So here's the thing to write down. The density of field lines in a particular region of the paper represents magnitude of field quantity in a region of space. I'm not saying it exactly the way it says in the final exam, but somehow it says that somewhere. I'll try to say it again. I'm saying magnitude of field strength somewhere in space is represented by or indicated by density of field lines on the paper. Yes, it totally. Oh, well, I can't. Okay, direct type person. I don't know about. Yeah, that's now me being a little bit, but yes, direct chat person. Yes, and good. Yeah, right. So what I'm saying to everybody, if you're looking at the final exam right now, and again, God bless you if you are, because like that's why we're doing it this way. No, thank you. That's cool. What I'm saying is, if you want to read a field line picture, and again, like this is so important. Weirdly, I know we're just talking about pictures, we're just talking about arrows, but like if I had to stop right now, if we all had to stop, the one thing you would learn from this, I think, is how to read a field line picture. And by the way, if you're and that's huge in physics. I mean, you could go right now, and I might even recommend if you go to Google Images right now, and you just type in field line or field line diagrams or field line diagram from electrical point or electrical dipole or anything, you'll see all these pictures that are actually really cool. They do look really cool. I mean, depending on what you think is cool, but they're super informative. Like it's an enormous amount of information in these field line pictures that once you know how to read them, like you have access to this whole thing. So what I'm saying here to everybody is the way to read or make a field line picture is magnitude of field is not indicated by length of arrow. No, it no longer. It would be in a vector picture, but in a field line picture, magnitude of field is not indicated by length of arrow. It couldn't be. All the arrows are all infinite. It's right. It's what Jacob just wrote. It is indicated by density. And by density, I mean density of lines on the page. So what I'm saying is here, look in this picture right here. Like this is a simple, and this is a picture of a field from a dot. I'm saying, look, like if you look here near the dot, there's a lot of lines per unit area. The lines are really close together. They're dense, they're thick. The field is very strong there. If you were to look out here, the lines are spread out more. The field is very weak there. That's how you, and if I were, and of course I'm just like sketching, wildly, but if I were computer generating these, or if I just pick up proper scaling factor and I'm very careful how I draw the arrows, then it actually like really works out quantitatively. Like you can literally do a one-to-one correspondence between the exact density of lines per unit area on the page, and that would tell you the exact strength of field in space. Okay, so from here on in, this is a new representation of how to picture how to picture fields, where from now on, so if you just go to Google Images and you type in
Question.
Oh, sorry. Yeah.
Does this have to do with the density at rates with the speed of light?
Well, we're getting there. Ultimately, it does. I don't think it ultimately totally does. If you're talking about the questions on the page, I haven't gotten there yet. I hope to within the hour, but so it ultimately does, but there's no way that could make sense to any of us right now, just based on what I just said. But so yeah, ultimately, yeah, but not yet, if that makes sense. By density right now.
Thank you.
Oh, okay. Thank you. Sir. By density, and hold on, let me just 1 second. Sorry. By density right now, I just mean on the piece of paper. So I mean, the closer the lines are, that means stronger field. Okay. And now I'm going to say, right, if you go to Google Images or whatnot, you'll see all these pictures of all these lines going everywhere in space. The way to read, great. The way to read those pictures is just like wherever you see the lines are representative, just like vectors. We're just picking, in principle, these lines are everywhere in space. Like you could draw as many, you could draw a million of them. But what we do is we pick a scaling factor. We say, like, for every 1 coulomb of source charge, we'll draw 5 lines or something. So then if you have a 2 coulomb source charge, we draw 10 lines or whatever. We're just picking a number, but then we're being consistent with it. And so if you look at those pictures on Google Images, if you have a moment, just check, again, just write field line diagram into Google Images. Wherever you see lots and lots of thick lines very close together, that means strong field. When the line starts spreading out, that means thin, weak field. Any one of these pictures, the lines would get farther and farther apart from each other as we get farther and farther away from whatever's causing them, because ultimately each space will have an infinitesimal field. So the reason this is all very important, I now want to start relating this to the equations and to life. Like, hopefully it sort of makes sense what I'm saying. This is a system, though, that I just constructed around like 1 point. I'm showing you what 1 point does. The whole purpose of all this is life is more complicated than 1 point. Like, we put lots of charge, just like we put lots of mass points together to make a planet, we put lots and lots of charge together to make wires, Van de Graaff generators, balls, spheres, like all kinds of shapes, capacitors made out of plates. So just a quick random example. Again, you can go to Google Images to do this, but like, okay, very quickly, just to give you examples. And again, it's actually best to just type into Google Images and see different examples, because my drawings are very primitive. Also, if you go to Google Images and type Yavrabam, you'll see tons and tons of Chegg answers from past years. I highly don't recommend that at all. But anyway, and they're all wrong. The guy made so much money off me. Okay, but so what I'm saying here is I've been drawing you just like points to make a point that hopefully is clear. But now, like, say we had a long line of charge, like a wire, but I mean a line of static charge, just like a bunch of protons like sitting there in a line. They would create field lines that would spoke out all over the place. Like what I just drew here is a cross section. It's a little bit deceptive. You really have to pay attention to what I'm saying right now, because I can't draw this well. But I'm saying that if you had a line of charge, the field lines would spoke out forever. So if you looked at it head on, you would see them radiating out. And if you turn the, so in other words, those red lines there are not meant to be actually parallel lines. They're not just all going up. They're all spoking out, right? Whereas if you had a plate of charge, the lines would parallel up, parallel out, right? Or and again, I recommend if you go to Google Images and type in dipole or something, here's one last example just to hopefully make it sort of clear. If you had like a plus charge here and a minus charge there, the lines could absolutely.
What does that say, Professor? On the side of the last image you drew?
Oh, down here, sorry. It says, right, from a plane, we would get parallel lines, or from a plate, I'm sorry, from a plate, we would get parallel lines. So,
Thanks.
no problem. Right. The thing I'm drawing right now is probably almost a waste, but there's no rule that the lines have to stay straight. They don't. They can totally bend. The lines will be, and so again, if you type into Google Images like dipole, you'll, in fact, should I do that right? Yeah, in fact, let me do that right now. Hold on. I mean, I'll share a screen. Give me 1 second. I think this will be worth it. Yeah, okay, let me quickly just, I mean, obviously you could do this on your own, but so that we can all. Okay, I just typed in field line diagrams into Google Images, but I just want you to see, like in the top left, and this, right, so it's just like the first hit, it's just random portrayal. But in the first hit to the top left is kind of what I was just trying to show you on my board. But then if you go over, you see these diagrams can get very elaborate very fast. First, so like in the next thing over to the right, the next picture over to the right, like what you have there is a dipole, is one positive charge next to a negative charge. And you see there that lines can bend and be curved. They're not vectors anymore. They're lines. They always go from positive to negative, and they can curve out, but they're as what they are. What I want you, and sorry, and then what you see like next to that is a positive next to a positive. They can start getting very, and then what you see under that in black and white is a positive next to a negative, but excuse me, in the top right, you see a positive next to a positive, but of different strengths. Like the positive to the right is like 3 coulombs of charge, for example, and the charge to the left is 1 coulomb of charge. What I'm trying to say, this is a lot to take in, I know. And again, you don't have to memorize any of these pictures or do anything, but I want you to see that each of these field line diagrams is on the one hand complicated and elaborate and curvy. It's not just vectors. On the other hand, each diagram is only as complicated as the situation is. That is, the lines are always the simplest, smoothest possible representation. The arrows are, the lines are always the simplest, smoothest possible way to draw a bunch of arrows that follow the rules that I said 5 minutes ago. In other words, as long as arrows are always starting at positives and going to negatives, and as long as the density of arrows indicates the strength of field, then given those basic 2 rules, the arrows will do the simplest, smoothest pattern they possibly can do to follow those 2 rules. So the arrows don't indicate how things would move. Like if you see these curvy arrows going from positives to negatives in the Google Images that I'm looking at right now, like in the red picture that's in the middle of the top row, the red picture that's complicated, that has curves in it, which is a positive next to a negative. I'm just making sure we're all looking at the same thing here. Yeah, it's a dipole. It's like a hydrogen atom. It's a positive charge sitting next to a negative charge. The arrows are going all from positive to negative. It doesn't mean that anything is moving from positive to negative. It means that anywhere you picked, if you picked any point anywhere in that picture and asked what would happen to some third party, to some test charge that was 1 positive coulomb of charge, if you pick any point, then wherever the arrows are pointing there, that's the way that test charge would be shoved at that place. And if you look at the number of arrows, that shows how strongly it would be shoved. So if you picked a point like way out here to the top left of that picture, arrows, a test charge would be sort of shoved out, but pretty weakly. But if you picked one in, it would be shoved over pretty strongly. And once it's shoved a little, then it's in a new space. So they'll be shoved differently. They're not lines of velocity. They're not lines of motion. They're lines of instantaneous force per charge. Okay. That's how to, and the bottom line is whatever the arrow is pointing, that's how you would be shoved. Oh, let me say this again too. Like if you look at the red picture, it's in the top row of the Google Images thing on your screen. So not the all the way to the left picture, but the second picture from the left in the top row. And you look at the complicated one, like the positive sitting next to the negative with all the curved lines in the middle. Please understand also, those arrows don't say what would happen to either of the charges in the picture. Both the charges in the picture are the source of this field. We're looking there at the field created by a positive next to a negative. In other words, we're looking there at the field created by a hydrogen atom, for example. So it's telling us what would happen if we were to place some other little proton in the neighborhood of that hydrogen atom. It is not telling you what would happen to the electron in the picture due to the proton in the picture, or vice versa. I hope that's sort of clear. Same with all these pictures. Field lines tell you what that object is doing to space in general, and the lines go on forever, just like the sun pulls everywhere in space, just weaker and weaker as you get farther from it. A hydrogen atom pushes and pulls everywhere in space, just more or less as you get closer or farther from it. So that's how to read a field line diagram. That's the idea of the field line diagram. And yeah, I think it answers hopefully one or two of the true false questions in the final exam. I'm going to switch screens back in a second. If I can. Pardon me, small break for a second. Okay, so now, so that's field line pictures. Now what? Okay, now I think the good news is, and you've all been very patient, and I see that we have like about a little bit less than an hour left. I'm sure that seems like torture. Again, you can go run and get a glass of water or whatever. In fact, okay, let's do it. My wife just asked me to get something. So I'm going to run and get a thing of water. You go take a quick break, just to take a breath, and then we're going to keep going. But I think we're on track here, because in my head, we now sort of understand how to picture electric fields through picturing field lines. So I can start relating this to those four equations. So I'm going to switch back. I'm going to switch the screens, and we can take a quick break. I'm going to run downstairs and get something. You can do the same. How do I? Okay. Yeah. So I will be right. We can take and I mean super quick. I'm just like running, just like use the bathroom or whatever. I'll be right back. Okay, so I know that was very fast. I'll pause for one more. Okay, I'm going to keep pressing. I'm going to go back to these equations now and tell you what they mean. I think they will start to, or at least I'm going to start with that first one. Oh, wait. Well, yeah, we're going to start with the first one. And if you can get the first one, they're all following the same model. So it's like anything else in physics. Once you get the thing, then everything else is like a layer around it. So that first law on the sheet here is called Gauss's law. It's saying something about electrostatic field. It's in fact saying something about electrostatic field lines. It's specifically asking us to look at what field does when it hits an area. Okay, this goes to a direct chat person's question or whatever, a direct question from someone in the chat. This left side of this equation the E, okay, that word, sorry, Juanita, I'm sorry to everybody, you can't, I'm sure you can't read that, I'm sorry. Okay, the E in that equation meant electric field, electrostatic field. And again, field means force per charge, right? I mean, again, field is just like the force as it was generated before it ever happens, if that makes it right. It's the force waiting to happen. By the way, analogously, potential, electric potential is just potential energy waiting to happen, right? It's the same idea. That's why I gave you that box yesterday. It's all about whether you're talking about what one object does to another or whether you're talking about what one object does to space. And we're all about at this point what one object does to space. We believe in that idea because we see objects communicating with each other through empty space all the time. All right, so anyway, the E is electrostatic field. The E dot ds is the dot product of electric field with a bit of area. It's field times area. It's field strength times a bit of area. It happens to be an infinitesimal area there, but then when you add up all the infinitesimal areas, you have field through a finite area, right? In other words, what you have on the left side of that equation, don't worry about the closed circle just yet. If there weren't that circle, the double integral of E with respect to ds is called electrostatic flux. Flux is stuff through an area. Electrostatic flux is electric field through an area. It literally means, the flux integral, and this is a big thing in math and science in general, you may encounter it again in other classes. A flux integral is just what happens if you take some vector or some quantity and you multiply it by a bit of area, and then you walk to the next bit of area and multiply the quantity by the area again, walk to the next bit of area, multiply the quantity by the area again, and add those, keep putting those products in your bag as you walk and add up all those little products. And now you'll have the total amount of stuff going through a total amount of area, right? It's an integral for the same reason that work is an integral, in that we're just acknowledging that there might be a certain amount of field strength over here in this bit of area, and there might be a different amount of field over here in this bit of area, so et cetera, et cetera, et cetera. So we want to add up the whole thing. We need a continuous function. We need to acknowledge the possibility of continuous variation through that area. So we use an integral rather than just a regular sum. Now, the flux integral does not always have to be closed. You can talk about flux. You can talk about electrostatic flux through any area you want. You could talk about the number, and you could talk about the amount of field going through some big table or something. Here we happen to be talking about the flux through a closed area. I'll get to that in a second. But the first thing I want to say about flux, I guess I do want to go to a new page here. Hold on a second. This whole flux idea . Okay. Oh, check. Yes. Okay. So quick, taking the direct chat. Right now, I'm saying E flux is the area integral of field. by definition, flux could be open or closed. You can have flux through an open area, and I'm going to get into this, but an open area, well, yeah, I'll get into that in a second, but yeah, it could be open or closed. It happens that the law, Gauss's law that we're saying here, is a law about closed flux. So I'll be more specific about that in a minute, but yes, flux in general is just field through area of any kind. And before I get into closed or open or anything like that, I want to say something about why do we care about flux? Like flux is a very strange, like why would we care about amount of field going through an area? We care about it. It comes from this guy, Michael Faraday, this Scottish high school chemistry teacher. He came up with the idea of caring about flux, and there's many reasons to care about flux, but one huge reason, and honestly, again, I've been teaching for like 20 years myself before I even really realized the thing I'm about to say right now. I mean, it blew my mind when I realized it, and I mean, I didn't make it up. I couldn't believe I had never understood the following thing before, which is that the reason we care about lines hitting an area, the reason I'm suddenly on the last day going to jump to like two-dimensional integrals is that field strength itself is represented by number of density of lines on the page. The number of lines per unit area on your piece of paper that you draw, like the more lines you have per area, the stronger the field is there, right? Okay. So field strength is represented by or indicated by density of lines per area. Field strength times area, what we call flux, is of concern to us, or it's a good thing to track. It's a really good thing to picture because flux means field magnitude times area. Field magnitude already was represented by number of lines per area. So flux is lines per area times area, which means flux, this idea of flux in space, of E field lines hitting areas in space, which might sound very abstract, is the easiest thing to picture on a piece of paper because flux, field magnitude times area, is represented on a page as number of lines per area times area. So the areas cancel out, and what flux in space, why it's important is because it's so easy to see on a piece of paper. It just means number of lines, period. Electrostatic flux in space is just number of lines that we drew on a piece of paper. So it's really easy to track and visualize. It's really easy to represent and see and follow without a lot of hard math. The person that made up this idea was a genius physicist who was bad at math in his own mind. I mean, I'm sure he was a lot better than I am and maybe better than some of us, but he wasn't as good as he wanted to be. And he really cared about physics, not just math. He cared about the physics. So he came up with physical ways of picturing physical things that were not all heavily quantitative. And there is supposed to be a difference between physics and math, right? So anyway, the point is that this seemingly very complicated mathematical looking thing, this double integral of the dot product, what it's about is just counting lines on a page. Flux equals number of lines, period. Now, okay, so we care about flux because when we care about flux in space, it means all we have to do is count the lines on our page. And we could say, oh, the flux is getting bigger or the flux is getting smaller just by looking at how many lines we have in a certain region or not. Okay, this is all thanks to Michael Faraday. Now, looking at the time, okay. Oh, okay, so back to this law. So Gauss comes along and uses this idea of flux and says, oh, wait a second. Wait, I'm just trying to think which thing I want to say first. Okay, Gauss says, picture a closed area. Like we can have flux going through any area. And I guess I should be, you might want to write this down. I don't know how you can write this down, but regions can be open or closed, right? Just like, and this gets into one of the true false final questions, I'm sure, or a couple of them. You know, we had integrals that were open and we had integrals that were closed because we can walk down lines that are open, or we can walk down a line that is closed, meaning comes back to itself. Closed means come back to yourself. Well, that doesn't just apply to one-dimensional regions. That idea of open or closed doesn't just apply to one-dimensional regions. It applies to two-dimensional regions as well. A two-dimensional region of space, an area, can be open or closed. An open area is like a piece of paper, which I totally do not have, of course. An open area is a piece of paper. Here's an open area. Here is a closed area. Here is a spaz trying to close a piece of paper. This is your brain. This is your brain on drugs. Okay, here is like a closed piece of paper. I wrapped the paper and its ends touched itself. It's closed in the sense that if I started walking on this piece of paper, I could keep walking forever without turning around, and I would eventually get back to where I started, right? It happens that the caps are open, but whatever. Just like you can take a string and it's open, or you can bend that string into the second dimension and touch its ends, and now you have a closed piece of string, right? So you can have a one-dimensional region of space that's open, or you can close it up. Same thing with two-dimensional regions of space. You can close a region of space so that it now is like a round trip in space, so to speak. I'm going to say this is totally now going to answer like 4 of the questions on the final exam. I almost should write it down because it's this complicated, but I'm not going to write it down. You're going to have to get it, and then you'll get 4 questions right. So I'm going to say, I'll say it a couple of times, but if I write it down, well, yeah, I'm going to say it. Okay, I'm telling you right now, it covers like 4 of the questions in the true false thing. So please pay attention. And obviously you can play this back later, but regions can be open or closed, I just said, right? They can also, okay, I'm going to say this, but this is not the thing yet, but they can also be bounded or unbounded. If a region is unbounded, it means it goes on forever. If it's bounded, it means it hits a boundary, a wall, a limit, an end, right? So like a line segment, so don't write this down yet, just pay attention for a second. A line segment is bounded at both ends by 2 points, right? Like a line segment is bounded. Sometimes you're on the line and then eventually you hit the end and now you're off the line. It's got boundaries. A line is unbounded. There are no boundaries. It goes on forever, right? A ray is bounded at one side and unbounded on the other, right? So similarly, an area like this piece of paper is bounded. There's a boundary. Sometimes I'm on the piece of paper. Sometimes I'm not on the piece of paper. There's a difference between being on the paper or off the paper. That difference is the boundary, the limit, the end of the piece of paper. But you could imagine, if you can imagine a line going on forever, you can imagine a plane, a Euclidean plane going on forever. That would be unbounded, right? So what I'm saying so far, and I am watching the clock, this does get dicey. What I'm saying right now is regions of space can be open or closed. They can also be bounded or unbounded. Not the same thing. Very related, very similar, very, yeah, okay, I'm about to get to that direct chat person. Yes, okay. I'm gonna try to say it a couple of times clearly, but then I'm gonna have to move on. But so right now I'm just saying in like the Venn diagram of our minds, we can think of regions of any kind of size regions, whether one-dimensional, it's always easier to picture one dimension and 2 dimensions, but whatever I'm saying should apply to any number of dimensions of space in some way or another. Regions of space can be open or closed. Open means if you keep going, you keep going. Closed means if you keep going, you'll end up back where you started, right? They can be open or closed. They can also be bounded or unbounded. That all sounds related, but they're not the same thing. Here's the relationship now. Here's the part you want to write down. Here's the part that's on the final, and believe it or not, totally relates us to electricity and magnetism. Here's the thing. And I think this almost is the thing in the final, here's the thing. A closed one-dimensional region of space, like a loop, right? A closed path, a closed one-dimensional region of space, or like an electrical circuit, a closed one-dimensional region of space is the boundary or bounds an open two-dimensional region of space, right? Oh, cool. Okay. I assume you're saying yeah, because I don't even know. Okay, cool. I'll say it again, or put another. Oh, no problem. Oh, that was to someone. Okay, no problem. I was hoping it was anyway. So a closed one-dimensional region of space, like the circle that my fingers are making, is the boundary for bounds an open two-dimensional region of space. Or put another way, here's an open two-dimensional region of space. It's open because it's not closed. It's open, but it's bounded. It's open, this piece of paper, and try to follow this. I can't say it too many times, even though it is a heavy idea, and it will link all the 4 laws together. But this piece of paper right here is an open two-dimensional region of space. It is open because it is not closed. It's not closed. I didn't wrap it on something. It's open, but it's bounded. It's open, but it's bounded. It's open because it ain't closed. Like the two-dimensional region of space here is open because it's not closed, but it's bounded. Its boundary is a closed one-dimensional region of space, right? The perimeter, this square path that walks around it. Like if I walked in this path, I would eventually get back to myself. So I've got a closed one-dimensional region of space that is the boundary for an open two-dimensional region of space. I know that sounds confusing. I mean, but you please write it down or think about it later. A closed one-dimensional region of space is the boundary for or bounds an open two-dimensional region of space. Right? Put another way, something can be open but still be bounded. And in fact, it is right here. So one last time I'm going to say it, and I'm going to say the other thing, and you'll see, and just like put it in your paper or put it in your brain or put it in the final exam. And then I've got like 25 minutes to actually relate it back to electricity and magnetism here, or I've got, 20. So what I said, I'm going to say it one more time, and then I'm going to say something similar but different to it, is a closed one-dimensional region of space bounds an open two-dimensional region of space, like always, like that's always true. Similarly, a closed two-dimensional region of space, okay, this is going to be similar but different. Be careful. Like what I just said was a closed one-dimensional region of space bounds an open two-dimensional region of space. Now I'm going to say, and again, obviously, if you didn't get that, you can play the video again and all that. I'm not like trying to be mean, but I'm just trying to, right? Just physics just gets heavier and heavier. Anyway, what I'm trying to say now is a closed two-dimensional region of space. Like I take this piece of paper and I close it up, and maybe I even close up the caps too. Or I take a map of the world and I close it up. So now I have like the surface of a globe, right? I take a piece of paper and I close it up. I make it like a surface area. I make it like like a surface area, right? Like I take a surface and I close it up. What does it do? It's the boundary to a three-dimensional region of space. But I'm going to say that more specifically. What I said before was a closed one-dimensional region of space bounds an open two-dimensional region of space. What I'm going to say right now is, and watch the words because they're not exactly the same. It's not a perfect analogy. It's not a perfect analogy. It's very close, but different. What I'm going to say now is a closed two-dimensional region of space bounds a unique three-dimensional region of space. Unique. And this will get us into the laws now, right? Like in other words, if I take a map and I close it up and make a container out of it, I close it up. So now I have like a container, like I have like the skin of an orange or whatever. Like if I take a map and I make it into like the outer skin of a sphere, now it is the boundary to a three-dimensional region of space, just like a loop is the boundary to like a flat disk or whatever. Now this skin that I just made out of bending a map is the boundary to a three-dimensional region of space, but I'm not going to call that three-dimensional space open or closed. Like three-dimensional, I mean, we live in a three-dimensional world. All regions of space that are three-dimensional, they're all open or they're all closed. I don't see the difference, but it is unique, meaning that once I talk about like the surface area of a sphere or any kind of closed surface area, any kind of closed area is a container. And it is the boundary to a unique, automatically identifiable, automatically recognizable containment, enclosure, right? A map is the surface area to the globe. And there's only one globe that fits inside that map. All right, so I'm going to say one last time, I'm going to move on and show you how it relates to the laws. And again, I am watching the clock. And again, I know none of this sounds like it all of a sudden sounds like I've just departed to talk about geometry. But the reason I'm doing it is, remember, we're trying to talk about fields here. Fields are how space contains and transmits information. So actually what we're finding out about is the nature of space. Like that's how this is all. But anyway, the statement one last time, if those of you who are still with me, your reward is, I think this is like probably 3 of the questions in the final exam. I'm saying they might be worded slightly differently, but I'm saying a closed one-dimensional region of space bounds an open two-dimensional region of space, and a closed two-dimensional region of space bounds a unique three-dimensional region of space. Okay, that's what I'm saying right now. Now I'm just checking the time. Okay. Now, how the heck does that relate to like these laws or whatnot? Well, this first law, no. I mean, good question, but no, I'm not saying that. I'm just going to relate to the direct, like open to, I'm going to say it one more time. Like I'm being very deliberate. Closed one-dimensional region of space bounds a open two-dimensional region of space, not necessarily unique for anybody who's paying attention right now. Whereas a closed two-dimensional region of space bounds a unique three-dimension. I'm not trying to be a jerk, but I am choosing my words very carefully there. So like, good question, but no. Or yes, or whatever. I mean, yeah, okay. All right, now, what's that got to do with? Well, Gauss's law says, oh, okay. So here's the deal. If you pick any, it's a closed integral. Gauss's law is a closed integral. It says if you pick any, yeah, no, I know you totally are. Yeah, wait. Well, right, I know, but I'm also, yeah, no, I know, I got you. Okay. So Gauss says if you pick any closed surface area anywhere in the world, in other words, and you might want to write this on the piece of paper, like the left side of that first law, Gauss's law, really what the left side is about containers. Pick any container in the world. Tennis ball can, like any shape of a container, it doesn't have to be a real container, but the shape of any container, tennis ball can, surface area of a globe, box, rectangular box. Gauss's law says the total amount of electric field emanating, the net amount of electric field going out of any box that you pick anywhere in the world, the total amount of flux is equal exactly to whatever amount of charge is enclosed in that box divided by a constant. And don't worry about the constant, just makes the units work out. So basically what Gauss's law says is that, what Gauss's law says is the net electrostatic flux, the net flux coming out of any container is entirely determined by nothing else except the total amount of charge enclosed within that container. Put another way, remember again, a closed two-dimensional surface bounds a unique volume. The minute I picture a container, like a box, a pyramidal box, a spherical box, the minute I picture a tennis ball can, if I picture a container, we all know what exact volume, like we can all picture the volume within that container. We would not disagree on what the volume is. Like a tennis ball can like contains 3 tennis balls. There's like no mystery about that. What Gauss is saying is, if you want to know how much field is going out through that container, all you need to know is the total amount of charge inside the container, and that will answer your whole question. In other words, and you might want to write that down, and it is a discovery, it is a big law. Gauss is saying the total amount of flux going through any container does not depend on the size of the container, does not depend on the shape of the container, does not depend on the shape or the arrangement of the charge within, does not depend on the shape or the size or the arrangement of any charge without. It only depends on the number of charges within. End of story. Total amount of electric field emanating, net fluxing through out of any container depends on nothing but the charge enclosed by that container. Okay, in a way, it's a big revelation, but in another way, what it's really saying is, if you remember that electric flux is just number of field lines, what he's saying is pick any container in the world. The number of field lines that's coming out of that container just depends on how many things inside started the field lines. Like the number of lines coming out just depends on the number of positive charges inside, because field lines don't start or stop spontaneously anywhere in space. Like once you picture field lines, the way we're talking about them, once you picture field line diagrams, field lines are conserved. They start at positives, they go on forever. So if you want to know how many field lines are coming out, I mean, look at this picture. Look at this picture, right? Like whatever container I pick, if I surround that point charge with a square, with a rectangle, with this circle, with a tennis ball, with a big circle, with a small circle, the flux coming out of that container is simply the number of lines that come out of that container. And what Gauss is saying was the number of lines that come out of the container is a number that you could totally know just by looking at what the charges are inside. Nothing else will change that number of lines because field lines don't start or stop in space. Now, so what? Why is that a big deal? Why is that law a big deal? Well, first of all, it starts to tell us how to picture electric fields. Field lines flux out through containers and they flux out of charges, and all that determines the fluxing out of these lines is the number of charges. Put another way, and you might want to write this down, what that says, like in a way it's obvious. It's just set, once you believe in these pictures, it's sort of obvious. It's just saying wherever you count the number of lines in a picture, you're going to get the same number wherever you count because they don't spontaneously start or stop anywhere on the page. It is kind of, and I'm going to have to, that's true. That's right. That's another question right there. Now I'm going to have to ask people to hold questions now because we only have like 20 minutes now and I'm going to be a little bit racing here, but I think we've covered a lot of the questions so far. I do want to get to the end. But what I'm saying is the first law, Gauss's law, in a way, if you're following all this, in a way, it's obvious. It's just saying, if you want to know the number of lines that emanate through some container, just count the number of lines. And wherever you count, that count is not going to change. But what that means in English is that field lines are conserved. They're never created nor destroyed anywhere in space. The number of field lines is all the same. That's another indication right there that fields are just like matter. They're real. Just like matter is never created nor destroyed. If you count the number of electrons over here and then they rush through a circuit and they end up over there, you better get the same number over there as over here because they don't just spontaneously pop into existence or pop out. Field lines caused by charges are just like charges themselves. In other words, information is conserved just like matter is conserved. That's in a way what Gauss's law is saying, is that field lines are conserved. They are as constant in space as material itself. That's another sort of way to understand the reality of fields, okay? That's what the first law, the Gauss's law, says. Now I have to race a little bit to get to the rest of the laws, like how they're all connected. The second law, finally, with 20 minutes left, gets us into this whole other thing called magnet. It's not a whole other thing, but this other thing that I haven't mentioned. Okay, so the first law says, and yes, this is one of the final exam questions. It says the net electrostatic flux out of any container is totally determined or directly proportional to the charge inside that container. To be honest, if you're still listening, when it comes to electrostatic flux, it's not always zero. You can have net electrostatic flux coming out of a container that's non-zero, but it's always fully determined by the charge enclosed. Okay. Now, the second law gets us into something called the magnetic field. I'm going to introduce it right now for the first time. Up until a certain point in history, we had two actions at a distance that physics understood anything about: gravity and electrostatics. Point masses pulled on each other, point charges pulled and pushed on each other. That's the end of, to a certain point in history, those were our two fundamental forces, or our two fundamental, those were our two fields that we understood. But people started playing a lot with electricity once these understandings were advancing. They've started playing a lot with electrical, like the voltaic cell was invented, circuits were invented in the late 18th century, early 19th century. So people started playing with wires and batteries and resistors in the lab, just like you are in the lab. And then this guy, Ampere, and some other people too, Biot and Savart, and this other guy, Oersted, they started playing with electrical wires and currents in the lab. And this you're gonna have to write down somehow. Well, actually, I'll write it really quickly. Okay, Oersted is one of a number of physicists who's playing with electrical wire, not playing with, obviously doing deliberate things with electrical wires and electrical currents in his lab in the early 19th century, like the early 1800s and mid 1800s. And he's one of many, but he's the famous one. He's got two current carrying wires nearby each other in the lab. Okay, two wires. First, there's a bunch of charges in the wire, but he doesn't have it. He turns off the batteries. There's no voltaic cell on at first. So it's just wires that each have a bunch of protons and electrons, probably equal number in each and probably equal to each other, but they're just sitting there and they don't do anything. Then he turns on the current. So then charges start flowing through the wires. He does it on purpose. And he on purpose sends current through these two nearby wires. He sends currents going in the same direction as each other nearby in the wires. And what he sees is that the wires attract to each other. They accelerate toward each other. This is a major, major discovery. And then he turns around one. And again, when the wires have a bunch of protons and electrons in them, and they have a bunch of mass in them, but they're not doing anything to each other noticeably. But then when he turns on the current, they come toward each other. And then he turns around one of the wires so that they go in opposite directions and they repel against one another. Now, this is a big deal. I'm saying this quickly, but this is a big deal because he says, wait a second. I'm sure this has a lot to do with the protons and electrons. I'm sure this has to do with electricity because like I'm playing with wires and all that. But wait a second. If it were just the electrical charges, so these wires are pulling each other through a distance, through empty space, right? It's action at a distance. And he says, wait, I know it has to do with an electric charge somehow, because like when I wasn't sending electrical charges through the wires, they didn't do that at all. And then I sent the electrical charges and then they did. But it's not just raw electricity. It's not the electrostatic force. It's not the electrostatic field that's going on here for a couple of reasons. One, when the charges were just sitting around, but they were there, this didn't happen. And number two, once I sent the charges moving through, not only it did happen, and in fact, it happened more the faster he sent the charges through, but very dramatically, when he sent the charges through in the same direction, the two wires attracted. That is not what we're used to happening with protons and protons, like charges repel. Protons and electrons attract. Here, you have protons or whatever kind of charges all going in the same direction, and yet they attract. So something funny is going on. This is the third action at a distance, or the third field that physics is now prepared to look at. The first was gravity. The second was electrostatics. This is now an interaction through empty space, right? Through empty space that certainly has something to do with charges, but it doesn't just have to do with raw charges sitting around. It's not electrostatic, because no matter how many charges were in those wires sitting around and existing, they weren't doing this to each other. And it ain't gravity, because no matter how much mass was sitting in those wires, the masses weren't doing this to each other. This was a new action at a distance that had seemed to have something to do with, or had everything to do with, the motion of charges, current, right? Which is not just charge, it's flow of charge. This was a field. This is an action at a distance, an interaction through empty space that seems to be being caused by current. It can't be on its own, or at least at this point, it cannot on its own be explained by gravitation or electrostatics. But it does seem like a field because it's action at a distance. So it's going to be the third field that physicists look at or try to develop a mathematical formalism for. He could have called it anything. He could have called it the Oersted field. He could have called it the Ampere field. He could have called it the Averbound field. But because in the rest of the world, in the rest of life outside of physics for centuries and centuries and millennia, normal people had noticed one other action at a distance that we've navigated ships by and made compasses from and made like children's toys from for centuries and centuries and centuries. Everybody in the world has known that a hunk of iron near another hunk of iron seems to be able to pull or push it through empty space. And iron is a metal, and metal has something, and metal is what we use to conduct electricity to, because this is the third action at a distance that physics is looking at, and it's the only left remaining action at a distance in the regular world that anybody else knows about. He takes a gamble, or physicists take a gamble and a hope, and they're like, all right, this third field we're going to start studying mathematically. let's call it the magnetic field, because there's one other area in life left that seems to be a field. Like magnets are action at a distance. Everybody's known about magnets for centuries, but nobody knows the math of magnets. Nobody has a physical picture of how magnets work or why. They just know that they do, just like with gravity. We know that things fall. It took till Newton to like work out the math of that. People have always known that hunks of iron pull on each other or push on each other. No one knows the math of it or the microscopic anything of it. So Ørsted and his colleagues are like, this field that we're now going to study in physics that seems to be caused by moving charges, by flow, let's call it the magnetic field, in the hopes that if we can understand it well enough, we'll ultimately be able to understand why hunks of iron do what they do. We're going to think it's probably connected because hunks of iron are made out of metal. They've probably got electrical currents or somehow going through, and it turns out to be correct. But it was a gamble. Just to be clear, we call this thing the magnetic field because it is a field, because it's action at a distance, and it seems to have something maybe to do with electricity and current and conductivity and metals. So they called it the magnetic field in the hopes that they could link all these ideas together, which they did. Okay. So, and they used a capital letter B for some reason. Actually, a very random reason, doesn't matter at the moment. But from here on in, the capital letter B, and I'm watching the clock, I know we have 10 minutes. The capital letter B stands for magnetic field. Now, it's a field. It's going to do everything that fields are supposed to do. It's going to, you know, like represent force acting on space. The thing about the magnetic field, like electrostatic field, is caused by charges sitting around. The gravitational field is caused by masses sitting around, existing. This magnetic field evidently seems to be caused by charges in motion, i.e. currents. The magnetic field at its raw base level is caused by a line of moving charge, a flow, a current. Okay. In fact, I'm going to skip to the third law. The third law here on the page, called Ampere's law, says just that. It's, well, not just that, but it says that. It says, where do we get magnetic field? Oh, and I'm sorry, and magnetic fields, if they are fields, are going to obey all the rules of field lines. Like we're going to draw magnetic fields with lines the same way we draw electric fields with lines. And it's going to obey all the same rules. It's just going to be whatever we find to be caused by a flow of charge rather than a sitting around pile of charge. So the third law says, oh, okay, magnetic fields are caused by currents. Just like the top law, Gauss's law, says electric field fluxing out is caused by charges. This one says magnetic fields are caused by currents. And just like the top says electric flux is caused by charge enclosed somehow, like the electric flux coming through a container is caused by the charge enclosed within that container. In effect, that's what the third law, Ampere's law, in effect says, only it's a little bit different. It's different dimensionality. It's different shape. Because now we have, according to this discovery, Ørsted's discovery, we now have something that the first time we have, again, this is the third kind of field. Instead of having a dot sitting around causing field, we now have a vector causing field. That is flow of charge. Flow of charge, current, first of all, is a line, not a point. Like in its simplest possible form, it's a line, not a point. Second of all, it has direction, like a current's either going that way or that way. And apparently it makes total difference which way you turn it, because when you turn the wires around, they cause repulsion, whereas when you have them aligned, they cause attraction. So we now have a vector causing field rather than a dot causing field. If field is supposed to be all the information of the thing causing it, right? Just like a dot of electrical charge caused field lines to radiate out from it, and a line of charge caused lines to spoke out of it, and a plate of charge caused parallel lines to spoke out. We now have a vector that's causing field lines to go out, and they have to obey all the rules of lines. Well, this vector is not going to, it's not good enough for a vector to cause lines that spoke out of it, because that's what a line of charge does. If this vector caused field lines that just spoked out, there's no way space could tell from those lines what direction this current vector was in, right? Somehow this current vector has to cause lines in space that carry the information through space of what this vector is doing. That is where it is sitting, like where it's lined up, and what direction it's pointing. Remember, we said field line pictures are the simplest, smoothest picture that conveys the information of the thing causing them. In other words, field line pictures are the smoothest, simplest, most symmetric picture of lines that could possibly depict the asymmetry, the difference of the shape that's causing them. So even though I'm going to say this fast and you may have to think about it, the only way a vector could cause lines that go everywhere in space, and lines that the denser they are, the stronger the field is, et cetera, the only way that could make sense is if the vector of current caused lines that loop around it. Okay, we're going to run out of time, so I can't draw this now, but a dot of electrical charge causes lines that radiate out from all directions. A line of current causes lines that loop around it. In other words, and this is now the, okay, in other words, and this is the second law on the page now. In other words, magnetic field lines are themselves closed lines. Magnetic lines loop around because they're not caused by dots, they're caused by vectors. Magnetic field lines are closed lines. If you draw any container in the world and ask how many magnetic field lines are busting out of this container, like net bust out, net flux out of any container, you will always find zero. That's what the second law says. You'll always find zero because magnetic field lines themselves are closed loops. For any line that goes out of a container, it will eventually come back in. That's what the second law is. So in other words, the first law is saying electrical field lines radiate out from points. The second and third law are saying magnetic field lines circle around, loop around vectors known as current. Okay, and again, now I know we have 3 minutes. How can I say that? So that's so magnetic field lines and electrical field lines. Electric field lines bust out, they flux out like this. Magnetic field lines loop around in closed spaces. Magnetic field lines themselves are the boundaries to open areas. Now, the final fourth law says, and it's a completely independent discovery, and it will be done. I'm watching the clock. I mean, and I apologize. I might go like 3 minutes over, but I will not go later than 4. And if you have to go, you have to go. I will not go later than 4. We go to 3:45. I may have to go to 4 to finish this, and I apologize. If you have to go, you have to go. But and then goodbye, everybody. I love you all. But so far, what we have now is just we have 3 fields in life: gravitational, and electrical, and magnetic. Electric field lines go like this. Magnetic field lines go like this. They loop around each other, again, because they're caused by vectors, currents. Faraday, the guy I keep talking about, Michael Faraday, comes across a totally independent discovery in something he's playing with in lab. It's totally crazy. He finds out, and it's a whole new law because there's no explanation for this. It just seems to be always true. And this is our last law, so we're just about done. He finds out this thing called Faraday's law, that if you have some open area, and you put magnetic flux through it, you put a magnet nearby, and you send magnetic field lines through the open area. If the magnetic flux, magnetic field through an open area, if you change the magnetic flux through that open area in any way during time, like as time goes on, in other words, if you make the area bigger, or you make the area smaller, or you make the magnetic field strength through the area stronger or weaker, or both, if in any way the total amount of magnetic flux through some open area changes in time, for some reason, that induces an electrical field in the closed path bounding that open area. Crazy, completely crazy. No reason it should be true. It just apparently is true that when magnetic flux changes in time through an open area, it induces an electrical field through the closed path bounding that area. In other words, a voltage. In other words, electrical current. In other words, this is electromagnetism. You've heard about it a million times. You probably just never thought about it in this geometric way. If you have a magnet and you bring it closer or farther away from some disk or some plate, you suddenly get electricity going in the perimeter of that plate. That's what this law says. You change magnetic flux through an open area, you get electric field induced in the closed path bounding that area. So, all come right. Okay. That's just a discovery. I'm not saying it should make sense. I'm just saying apparently it's always true. And it's Faraday's law. So now magnetic field lines bound currents that cause them. Electric field lines like bust out of charges. Apparently electric field lines can get induced or caused if the magnetic field through the area that they bound changes. That would be and that, by the way, that last law, Faraday's law, I'm saying in a very complicated way, and I see it's 3:55. Again, bear with me. I will not go more than 5 minutes over this, no matter where we are. And I'll look at anyway, that last law, I'm saying in a really weird way. You've heard about it before. That's just the whole idea of electromagnetism. That is what a generator is. It's like we just rotate magnets around and around. We keep changing magnetic field through an area, and then electricity is induced by that. It's like the beginning of the Industrial Revolution. It's a huge discovery, right? And it just is what it is. It would be the end of the story. It would be that we have two laws about electric fields and two laws about magnetic fields, and they're linked together in this electromagnetic way that allows us to make machines and generators and all that, except for one thing. And this you have to write down. If I start writing, I'm going to get bogged out. But that would be the end of the story, except in 1879, there's a man named Maxwell, James Clerk Maxwell, who looks at these laws and looks at the math and develops all this math behind them, and looks and says, and I'm going to say this quickly again, but he says, wait a second. These laws are too similar. There's too much symmetry going on the left side. Like it's two pairs of E laws, two pairs of B laws, two pairs of closed surface area integrals, two pairs of closed path integrals. There's too much damn similarity going on the left side for the right side to be such a jumbled mess as it looks right now. And Maxwell says, and please bear with me again for 4 minutes, but Maxwell, James Clerk Maxwell, 1879, looks at these laws that are just like flying around, and they're not written exactly this way at the time, and there's other laws too, but he looks at these laws and he says, wait a second, something is going on here. Because you know what? Even though a closed surface area bounds a unique volume, a closed path does not bound a unique area. He says, and I'm going to say this really quickly. He says, wait, what if I send current going through what if I send current going through a capacitor or something in circuit where what if I send current going through some region of space where I change the amount of current during the time, like I had a time dependent current, like I made the battery stronger or weaker or whatever. And I drew a circle around the current that was going through to look at the magnetic field going through the circle around the line of current going through. According to the third law, Ampere's law, the amount of magnetic field I would get in this loop around that current is exactly determined by the current enclosed. And current enclosed should mean the amount of current going through the area bound by that circle that I just drew. But he says, but wait a second. I can draw a circle and think of it as like the skin of a balloon. I can think of it as the skin of the balloon, and the balloon is like the area bound by that circle, but I could blow up the balloon and that still is area bound by that circle. In other words, you can stretch out the area that's bound by a closed path. The open area bound by a closed path is not unique. You can picture other areas going through, and you could design a situation where the current gets caught, stored, where charge gets stored in something called a capacitor, like in that balloon. And because we picked a funny area, Maxwell's being really, really picky, really, really weird. And he's like, we could pick a funny area that's still technically bound by that balloon, that's still technically bound by that loop. And therefore we would get no current going through there, but we would still have magnetic field. So something is missing in that law. Like it's a really obscure argument. And it's also for mathematical reasons that he developed on his own. But he says something is missing in that third law about magnetic field being induced in loop. And he says, I believe that there's an extra term that has to go there. And you can write this down or not. He says, I believe that just the same way, and we're just about done. He says, I believe that just the same way, change in magnetic flux just in the same way that the change in magnetic flux through some open area induces electric field in the closed path bounding that area. I believe that it must be the case, if this third law is really universal and really takes care of all areas bound by all loops, it must also be the case the change in electric flux through some open area must induce magnetic field in the perimeter of that area. Crazy. I'm not saying that you should say, I totally get that. That totally makes sense. No, it's a big leap. But for mathematical and really obscure geometric reasons, he says, I believe there's a term missing in that third law. I believe that the time rate of change of electric flux through an open area should be added to the right side of the third law, and it should induce magnetic field in the boundary of it. And what that means, and we're done, but what Maxwell realizes is that just as changes in magnetic field induce changes, just as changes in magnetic field induce electric fields, it must also be the case that changes in electric field induce magnetic fields. He basically realizes because the left side of all these laws is too clean and symmetric for the right side to be so unpatterned as it is. So he says there must be a pattern. It must go both ways. And what that means to us and to life in general is he realizes that if you set, I'm going to say this is it, okay? Current causes magnetic field. Changes in magnetic field cause electric fields. Electric field causes current. If you, and etc. One causes the derivative of the other. So if you set up, this is my last 2 minutes, 1 minute, I really apologize. If you have to go, you have to go, but set up a current that is a cosinusoidal function of time. For example, set up a current that's a cosinusoidal function of time. That current will create magnetic field. The derivative, and if you change that current, then you have a derivative of that current. It changes the magnetic field. Well, the derivative of cosine is negative sine. So then the magnetic field will change. If it changes, it'll cause an electric field. But the derivative of negative sine is negative cosine. So it will cause a change in magnetic field. As you all know in this class, the derivatives of sines and cosines can be taken forever, forever, forever. So if you set up a cosinusoidal, for example, current, it will make a magnetic field that's changed. If you set up a cosinusoidally changing current, it'll set up a magnetic field that's sinusoidally changing. That magnetic field will, because it's changing, will cause an electric field, which is sinusoidally changing. That sinusoidal electric field will make a magnetic field that's so sinusoidally changing. And each one will cause a field that's in the back. Each one will go through an area and cause a field that's in the boundary of that area. And each one will therefore be perpendicular to the next, and they will keep causing fields that will be perpendicular to the next and eventually run out of space and leave the current that you made in the first place. Like a cosinusoidal current will make a cosinusoidal field, which will make a cosinusoidal field, which will make a cosinusoidal field, which will make a cosinusoidal, and the fields will leave the current and propagate off in space in a manner that satisfies the wave equation that we developed. Like the cosines will make the cosine, it'll be a collection of staggered oscillators, like we were saying in the middle of this class. I obviously can't prove the math to you right now, but what I'm saying is, as long as we believe that changing magnetic fields make changing electric fields, which make changing magnetic fields, then cosines will make cosines will make cosines, and the fields will propagate off in a manner that totally satisfies our partial differential equation known as the wave equation, and the fields will wave off, leave the very current that made them. So, and I swear, I'm sorry I'm taking so long, but I really am just about done. What I'm saying is, like, force was me pushing you, field was me pushing. When a field can leave me and just go off and just be push. Not me push you, not me push, but just push that goes off in space and satisfies the wave equation. Or remember, in the wave, like these can be decoupled to make a wave equation out of the electric field or the magnetic field. And remember, in the wave equation, there's that constant term that is the speed of that wave that depends just on the parameters of the medium through which it goes. Well, the medium through which this wave goes is the electric and magnetic fields of space. The speed, those parameters are constant, epsilon naught and mu naught. This thing will leave this thing, these electric and magnetic fields, which are causing each other and radiating each other, will propagate out like a wave, like a ripple of staggered oscillating cosines. It will leave and travel through space as a wave at a speed which is constant and independent of anything else around it. And that speed turns out to be 1 over the square root of epsilon naught times mu naught, which is the speed of light. which you've probably heard before, but it's true. In other words, when electric fields and magnetic fields induce each other perpetually through like a perpetual cosine, infinitely differentiable cosine function, they create a wave of electricity and magnetism, which propagates through space at the speed of light. And what that is the information moving through. It's the vectors of space, the field lines of space, rippling, like sending the new information of whatever's going down here to over there. The rate at which field information travels is the speed of light. What the speed of light is just the rate at which information from one bit of space is sent to another. The speed of light is the speed of information. It is the speed at which the universe talks to itself. It's the speed at which one bit of space communicates anything that's going on there to any other bit of space. What it is electric fields and magnetic fields inducing each other so perpetually that they leave the original source that created them. That's it. That's the test. That's the course. I'm sorry to rush. Thank you for waiting so long for this. We're done. If you have any questions or any problems, please text me. I'm going to go now. I'm not even going to wait. I'm going to go. But thank you. You've been very, very patient. You've been a great class. Thank you guys so much for a great semester. Seriously. Okay. Thank you. Okay.
Thank you so much, Professor, for everything this semester. Appreciate it.
Thank you very much. No, I appreciate it. You guys have been great. I hope to see you
Thank you,
again. Thank you guys very much. Okay. And I'm totally going to leave. Yes. See you. Totally see you.
Have a great one.
You too. Have a great one.
Good luck with your moving.
Oh, and I forgot to do a game thing today. No, you guys are the best. I think there's no game. There's no more work of any kind. Just do whatever work you have and hand it in. Okay. You got till Saturday. Oh, I got to post the final. Thank you for reminding me. I'm going to post it like right now, I think. Okay.
Thank you, Professor.
Thank you guys very much. Okay. I'm going to leave right now. Oh, thank you for the, okay. Thank you guys. Okay.
Professor, can I email you if I have to speak to you real quick?
Yeah. Yes. Or you could text me, but yes, absolutely.
Okay, got it. Thank you.
Thank you. Okay. Bye. Thank you guys. Yeah, it's been my pleasure. Seriously. Okay. I'm totally